Hello, David.
Say hi. Nice to
Hi,
see you.
nice to see you. So, uh, welcome.
Yeah, thanks.
At least I have here the letter Moscow State University,
Excellent.
supposed to be the host of the meeting.
Yeah, I was looking forward to the original plan before the pandemic hit. I'd been in Moscow for a meeting in the almost 30 years ago.
Wow, oh, you would recognize Moscow. It's completely
Yeah,
changed.
it would have been great to see the differences. So.
But what we hope now that we will have to make again the conference in Moscow in normal way.
Yeah, I think things are all getting back to normal. It's just been it'll be a while.
Okay, good. So, David, we have your lecture, and I will announce, and then help with questions because people will. You see, you know how it works.
Yeah,
Uh,
yeah.
I will get from YouTube from translation the questions, or someone can also join here in the Zoom and ask here, and up to 1 hour, and depends on how much time you get for lecture. We will have some time for questions.
Yeah, I my hope is I can get through the presentation part of it, and I'm going to shoot for about 45 minutes.
Okay, okay, then
Hello, Deb.
Hey, Alexei, how you doing?
Yeah, I came to Moscow a few days ago for the conference, but
I did.
yeah, but then everything was closed. So then,
So you're just at home.
yeah, I just at home. Yeah, but still, it is good because we still have winter in Svalbard.
Oh, really?
Yeah, we had snow. Yeah, when
Oh, God. Wow.
yeah,
is it typical for Svalbard at this time to have snow?
no, it was this year. It was extremely long.
Ah,
Not
that's
yet.
unusual.
Yeah, unusual.
Okay, now you can enjoy rains in Moscow.
No, yeah, but I really was happy when I came to Oslo first day. I was really happy. Just first hours. It's best feeling over my maybe last 5 years because of warm and good weather. So then,
Yeah.
uh,
What time, David, you have now?
I've got about 18 minutes after, something like that.
So 4 hours difference.
how is John Dempsey doing?
Good, I guess. I've had a few email exchanges with him, but I haven't seen him in a long time. Um, it was kind of interesting, though. I've been working on uh, the results with that project of Artu Polyarvis at Alto, and some interesting things have come up, and I've bothered John to try to get at some of our really old, like 30 years ago, in situ data from Barrow, Alaska. And we took cores and did a lot of lab testing, but I don't have much of the in situ data. We did tests on floating ice plates up there, and so he's digging through his archives trying to find some for me.
Yeah. I was in contact with Dave Sodia. I was impressed that he was traveling in California.
All right. That would explain why he hasn't gotten back to me. So, yeah, he seems to be doing well. And I'd been, in preparation for this talk, I'd been having a few email conversations with him about his work, and which were very helpful. And sent him a copy of the paper probably just when he was leaving for his trip. So.
Yeah.
David, I think we should start now. And
Okay.
yes, and from this point we'll start the translation on YouTube. And okay, good day, everyone. And we continue now the OAK 2021 conference. And this second day of the conference, the plenary lecture will be done by Professor David Cole. And it's my pleasure to invite him to deliver this lecture for the next within 1 hour. And so we have the translation in YouTube, and you are very welcome to in the chat to send us the questions. They will be then read to the speaker. So David, you're welcome, please.
Okay, Sergey, thank you very much for the introduction. And I would like to express thanks for the invitation, originally from Alexei Marchenko, and to the organizers who have put up with my very much behind schedule submissions and everything, but they've been very helpful and understanding. So very much appreciated. With that, let me try the screen share. And is that working, Sergey?
So we now see your screen, but yes, and now we see your presentation as well.
All right.
Yes, it works.
Are we good then?
This is good. Excellent.
Okay, great. Okay, so there's my topic. I've been working in ICE since pretty much the beginning of time, I think. My first paper came out in the late 70s, and currently retired from CREL, but still active in various aspects, mostly of ice mechanics. I'd like to start out by just acknowledging a few people. This goes back many, many years, but my PhD advisor, Hans Wertmann, passed away about 3 years ago. I got to give a nod to him because in the 60s, he actually came up with the drag control mechanism for dislocations in ice that plays a central role in my model development. And then working many years ago with Anthony Gao from the lab, Glenn Durrell, who basically was the guy that ran virtually all the experiments that I've ever published at CREL. John Dempsey, of course, Clarkson, many years of field and laboratory work with John. And more recently, Alexei Marchenko, been working with him, kind of keeping me engaged in sea ice topics, which I very much appreciate. And again, in recent years, I've been working with Arttu Puolajärvi at Aalto on a sea ice project that's been a lot of fun and very productive. And Arttu put me in contact with Heo Hendrikski at Delft, and you'll see how he has played a role in what I'm going to be talking about today. Basically, we have just struck up a collaboration in the last month or two, but it's turned out to be very, very informative on my end, since ice structure interaction is not my main area of study. My sponsors through the years, and this goes back many, many years, the Office of Naval Research, the National Science Foundation, and then my home institution where I worked for 40 plus years, CREL. Okay, that being said, why should you even pay attention to what I have to say? My main theme here is what I'll refer to as anelastic enlightenment. There is a process called anelasticity. It's due to dislocations, primarily in ice. And that provides a time-dependent but recoverable component of deformation that figures very prominently into what I'm going to be talking about today, but more specifically of interest to the POAC community, I believe, is the fact that this mechanism actually provides a way to store and strain energy during load up, and then as unloading occurs, this mechanism dumps strain energy back out of the ice. What that does, as long as your ice is maintaining contact with the structure, is it actually puts this little push back into the structure as this anelastic strain is released. It looks to be a very prime candidate for a mechanism to support ice-induced vibration or self-excitation. There's a lot of different terms. I'll try to avoid negative damping, but it's the concept is out there and should be addressed. At any rate, that's the direction we're going. Now, when I was preparing for this talk, I went through my data archives and found some results, some of which you see here from 1990. And I'm embarrassed to say that I can tell from my file dates, I looked at these results then and then in the mid 90s, and that was it. They have sat there and followed through on all my archival data banks for years. And I ran across these results in preparation for this talk and was really surprised to find the results you're seeing here. And just briefly, what we're looking at is the stress applied to the sample is a ramp at a given rate. It's either 5 or 10 pascals per second, applied periodically to the sample at increasing peak stress levels. So just ramp up, ramp down, wait a bit, ramp up, ramp down, et cetera, et cetera. And there'd be a lot of intermediate load ramps in between times. And down here, what we see is the stress strain response. The first few at a couple MPa, not much loop area. It looks almost elastic, not quite. What's happening as we go to higher and higher stresses is that we're imparting more and more damage, microstructural damage to the ice, and also loading it up with dislocations, as it turns out. And just prior to failure, eventually there's a high enough stress that you fail the sample in a couple seconds, and it's a very explosive kind of failure. But while it's damaged and still intact, and this I was very surprised to find that there's this very large component of anelastic strain that you see basically realized after the load's starting to decrease. The strain hits its peak, in fact, in this case, about a quarter second after the load peak. And this level of strain, which is in the 10 to the minus 3 order of magnitude, is very, very large for this process. So it was actually very surprised to see it. But it occurred to me in looking at these results that this would be the kind of mechanism that could possibly provide the strain energy that's needed to essentially affect negative damping or provide a source of energy back into the structure from the ice. And so it's worth pursuing. And so what I'd show you now then is we're confronted with trying to model this behavior, which, spoiler alert, is in fact due to dislocation and elasticity, but let's build up to that point. So if the red curve here is the actual response from our specimen, nothing theoretical about this, it's actually observed. I don't have an awful lot of experiments, but enough that it's a reproducible phenomenon. when the ice can sustain this amount of damage. So if you had no dislocations in your life, and we're trying to model this with an elastic process and viscous, let's say, or damage process that would allow some permanent strain. There's a weak grain boundary relaxation. We won't worry about that too much. It's a lot faster than our load application. So it looks like it's in phase. So it just looks like a slight decrease in the modulus. But I wanted to just leave that in there. But no dislocations. So in terms of strain time, you would have your deformation would follow in phase according to the modulus in how much viscous straining occurs. With applied load, there's no out of phase component. You can see you would very much miss the behavior. You could say, all right, let's try a lower modulus to get the slope up, but you'd never capture the time-dependent piece of this behavior. So let's introduce dislocations, but a low dislocation density, 2×10⁹ per square meter. We'll get into what that really means later on. So now we're calculating a low dislocation density response. We see we're a bit off the original elastic curve. We can then, but we're not there yet. The only thing I'm doing in these calculations is increasing that one quantity, the dislocation density. Let's double it again to 4×10⁻⁹ per square meter. We're getting better. Let's go to 6. And we can see now with a high enough dislocation density, we're actually acquiring the shape of the response curve that we're after. And it turns out 8.2×10⁹ is pretty much the magic dislocation density that is reproducing the experimental observation actually quite well. It's a little bit off on the tail, but in general, it's capturing the basic sense of that time delayed behavior. So once I ran these calculations, and I got to say, I was shocked, pleasantly shocked, but still very shocked that this regime with fast loading, which is quite different from the conditions for which the model was developed, still handles this result to a certain point. I'm not to the point where I can predict yet what the dislocation density is under certain loading conditions, but I know that once I develop that relationship, I can actually handle these results and model it pretty effectively. Okay, so let's talk very briefly. I'm not going to try to make you experts in dislocation mechanics, but just for the record, what we're talking about are linear defects. So picture an extra atom plane kind of inserted into the atom plane. So it's almost like a half a page stuck into a book, okay? There's a linear defect at the end of our half a page that provides a discontinuity in the lattice. If we look at that as a plane of atoms that's been inserted, we get this sort of thing down here with my little set of matrices here. The dislocation would be, here's our extra half plane under a shear stress, and with the breaking and reforming of atomic bonds, this extra plane and our dislocation core that we're dragging along moves through the crystal. Now, if it's just moves part way and stops, it's under the influence of some internal stress fields that would in fact cause it to move in the opposite direction if we were to remove that applied shear stress. If there's enough time for the dislocation to move all the way to the end of the crystal, that gives you one increment of permanent or viscous deformation. But the case where it remains in the crystal and rebounds under the internal microstructural stress field, that's the process that gives us this anelastic behavior. And there's plenty of evidence that observations using a transmission electron microscopy. This image up on the upper left is a little fuzzy because it's difficult to do these in sea ice. But all the black lines are dislocations. So there's plenty of evidence of a lot of dislocations in sea ice. And so that gives rise to a very strong anelastic component. So physically, there's no issue with the concept of a lot of dislocation activity in sea ice, even unstrained. If we look at in freshwater ice, where things are a little more clear, a colleague down at Dartmouth, Ian Baker, has produced some just marvelous micrographs with showing dislocations being produced along grain boundaries. So all these black lines are individual dislocation cores that we see emanating out from this darker area. Here is a grain boundary where the stress concentrations are high enough to actually generate the dislocations. Here's another image a little farther back. All these tangles of dark lines you see associated with the ledges along the grain boundary are in fact great numbers of dislocations being pumped out from the shear stress along this grain boundary. So again, there's really plenty of evidence of the existence and in great numbers of dislocations in ice. So it's basically a well-established phenomenon. And so what I'll be talking about is how I quantify and model these the dislocations in ice and answer the questions that I posed initially, which is what's going on in these ramp loading experiments. So I always like to show a slide like this just to get us all thinking about our material. In our field work through the years, we've come up with a method to cut and remove these full thickness slabs that give a very nice view of the overall floss structure. Kind of hard to see scales. These are 10 centimeter increments. So this is about a 1.4 meter thick slab. This is about a 1.5 meter thick slab from Antarctica. You see horizontal banding. The banding features due to variations in brine porosity and mostly growth rate variations up top, but then that once the sheet gets kind of thick, they're going to be coupled with changes in current and such under the ice that also help govern how brine inclusions develop and form these layers. Also, very dramatic brine drainage features we've seen quite a bit in Alaska. Here's a transverse section. All these whitish areas are actually regions of high brine porosity that have drained out. Very important for overall mechanical processes, but won't be getting into that too much today. Microstructurally, we've always paid a lot of attention to our thin sections and density and salinity profiles through the sheets when we've done field work. Generally, sort of a granular layer up near the top, maybe 10, 20, or sometimes more centimeters that basically forms during initial freeze up. Once the congelation ice starts, you get this columnar growth, typically with increasing grain size with depth. When there's a current, under ice current that's prevalent for most of the time, then we'll actually get an alignment of the C axes of the grains that are growing. And I'll talk a little bit more about that later on. So that's our material. If you bring a microscope along in the field, you can take micrographs such as this. This is simply to get a good picture in your mind of what happens with temperature changes in sea ice. -3, very close to the melting point, about a meter down, which was near the bottom of this particular sheet. I was able to make a micrograph at almost exactly the in situ temperature. So this is what the brine inclusions, all these little shapes here along this sort of diagonal direction are in fact brine inclusions. It's drained out a bit, so you'll see little bubbles here and there, but just an incredible volume of brine at high temperatures. drop it down to -15, and we see this very much close off of all our brine inclusions, just because of the equilibrium conditions for brine in the ice matrix. This process is it's kind of interesting to look at. It turns out that there's some things going on with the influence of this aspect of the ice matrix as a function of temperature on the overall elasticity of the ice that I'll talk about in a second here. But this is mostly, for the record, is the development of the initial dislocation-based anelasticity model. Was back in the 90s. We then expanded, looking at, once we started doing field work and getting into aligned ice, we brought in alignment effects, developed a more sophisticated viscous straining component about 20 years ago. And then as one of my retirement projects, I've been kind of revisiting some of our results and realized that I could, in fact, extend the model virtually up to the melting point for freshwater ice. And that was a paper that came out last year. This is mostly so you can see what all, just for future reference, if you want to go back and see how things came along. So let's talk about the model for a bit. I'm modeling things in terms of strain and the components of strain being elastic, which is kind of obvious, but it's turning out to be a lot more interesting and complicated than I had given it credit for. I've got two anelastic components. The main one we're talking about today, which is this dislocation one, a grain boundary anelasticity, and then a viscous component. The elastic modulus is something I don't tinker with. It's just as a result of the physical properties of the ice, starting with the single crystal elastic components, and then incorporating brine and gas porosity effects. The two mechanisms, this drag-controlled dislocation anelasticity, grain boundaries offer a small but still relevant component of anelasticity. And then a single mechanism, which is basal plane dislocation motion, which was the original model inspired by this Wehrmann paper. Now, how do these relate to the physical properties? Well, elasticity, weakly dependent on the crystallography. It turns out that for sea ice, there's a very strong dependence that is in fact different between lab experiments and in situ experiments. We don't exactly know why, but I'll show you this fairly dramatic change in elastic behavior between the two cases. But all these other components are dislocation based and are therefore strongly dependent on the crystallography as it relates to the shear stress result on the basal planes, because that's where all the dislocation activity is, and dislocation density. Brine porosity just as grown, we see this increase. We don't have a huge range here, but as the brine porosity increases in the as grown material, the dislocation density increases for reasons that we can quantify but don't completely understand. Now, a quick note on stress dependence. The elastic behavior is linear. This second thing is a little bit unusual in that for the dislocation-based processes, both the anelastic and viscous components are linearly dependent on stress when there's a constant dislocation density rho. Most folks are expecting anything to do with ice and viscous strain rate will have an n equals third power law dependence. That is true only when your stress is increasing the dislocation density. Happy to talk about this more in detail, but just in the interest of time, I'll just state this to be supported if there's any issues. You get the third power law behavior when the dislocation density increases with stress because of this relationship. That dislocation density increases with stress to the second power. Once we see the viscous strain equation in a little while, you'll see why this then multiplies an extra power of 2 on top of this linear dependence. That's what gives you this n=3 power law. So, all right, let's, I want to get this out there. We're still thinking about this and trying to understand the underlying mechanisms. But let me just state this as empirical observation that when we do experiments on either laboratory prepared saline cores or sea ice cores that have been transported back to the lab and tested, we get this red curve for the behavior of the modulus as a function of brine porosity. Now, what I'm plotting here is just a modulus factor. So this would be whatever temperature dependent and crystallography dependent modulus you have for the pure ice case. You would then apply this factor to get at what the brine porosity effects would be on the pure unrelaxed elastic modulus. When we started taking a careful look at our in situ results over a fairly broad range of brine porosities, we found a much, much lower modulus. This is a factor of almost 4 out here at brine porosities associated with in situ kind of warm ice temperatures. So why that is, I've got some thoughts here. Again, it's all kind of speculative at this point, but this is what we've seen. And the work coming out of Artu's group at Aalto, where we're testing small scale but floating ice samples, we're starting to see this sort of behavior. That the work is still in progress, but I think within next maybe couple months you'll see work coming out there. But there's something about ice warming up as it's floating. There's just a more dramatic effect on the ice matrix of higher temperatures and loss of ice matrix in that floating ice situation versus a dry isothermal sample. So let's talk about the inelasticity. I don't want to get everybody too cranked up about these messy looking equations. Take a step back and think of what we're actually doing, how we're accounting for this analytically. And what we're doing is inelasticity is a time-dependent process. And if you were to use a standard sort of inelastic solid single relaxation time analysis, you would find a time dependence that would follow this orange curve here where I have alpha equals 1. That's in material science circles, that's a Debye relaxation process. It turns out that if you have one relaxation time invariant for your sample, this is the behavior you get. When you have a polycrystalline material, each with its own relaxation scale, variations in grain size and length of basal planes, etc., you actually have a distribution in relaxation times because you now all of a sudden have a coupled system of relaxing elements. And there's a clever way that I found it's actually in a footnote in the Noack and Berry Inelasticity and Crystalline Solids book from 1972. It's the only textbook where I found this relationship. And the beauty of that is it gives you a one parameter term to account for a distribution of relaxation times. Jumping track, and the paper covers these other topics in more detail. My colleague at Corel, Devin O'Connor, numerical modeler, basically implemented my constitutive model in Abacus. And Abacus can't unless you write a user generated subroutine for the material behavior, you're kind of stuck with what's called a Prony series approach, where you essentially determine a number of specific relaxation times, a spectrum thereof, that each have this single mechanism behavior. And it takes like 10 of them to reproduce what ICE is doing. It's a way to handle this numerically, but it's if you're just trying to develop analytical expressions where you want to go back and forth in, let's say, between frequency and time domains and handle things without a big numerical process, it's this use of this peak broadening term is the way to go. At any rate, so two things going on. One is how the process is realized as a function of time, governed by this normalized creep compliance function, and then how much strain you actually get out of that process, which is governed by this relaxation strength. So both the grain boundary and dislocation relaxation has a characteristic, a central relaxation time determined by the kinetics of the process and temperature, and a strength. And so the strength for the dislocation process is what's a linear function of the dislocation density. And I'm not sure if you folks can see this. I sort of have this blocked out by some little side video blocks here, but at any rate, this is a function of the orientation. It's a function of the overall process is a function of temperature through this relaxation time. Again, that my 1995 paper expounds on all this business, so we don't need to get into this. But basically, the central relaxation time for this process would slide to higher and lower times depending on the temperature. That's how that's handled. Okay, so just to show you that it does in fact work, some data from back in the old days, model predictions for 0.6 cycling MPa stress at -30 as a piece of sea ice. And these are experimental results for those same conditions. It does a fine job of handling. I'll note that this original development was all in frequency space, and then in more recent years it moved into time domain for these applications. But it does a good job handling like effective modulus as a function of temperature and frequency. Here we did some Haversine loading and tension and compression, and it misses here a little bit. I suppose one could fine tune it, but just using the model as such without trying to tweak it for a given sample, you really get pretty reasonable results with it. So having that model allowed me to then use the anelastic model to track how the dislocation density increases, let's say during a creep experiment. And so the basic test would be apply some cycles, get a hysteresis loop area, calculate the initial dislocation density, and then run a creep experiment for a little bit. Unload it, apply your cycles. Analysis of these guys tells you how much the dislocation density increased. And on we go. This plot over here shows you that doing this stage creep test does in fact produce an n=3 power law dependence. So it gives you a valid test result. And after about a year's worth of experiments as a function of stress, strain, and temperature at ice type, we were able to develop the relationships we'll be looking at in a second, which lets us track the dislocation density as a function of those variables. This just shows you what the hysteresis loops look like. And you can see the loop area is increasing with strain history here, and that's what lets us track the dislocation density. If we're looking at time domain behavior, constant load creep test, this is the kind of result that we're talking about, where there's an anelastic strain or an elastic strain, let's say when we unload, this time-dependent anelasticity, and then a viscous strain component. And so generally the model does a nice job on handling all that behavior. The 2020 paper I mentioned, this is quick results here. This really focused on the creep component. It was targeted for the glaciological community. So the ice mechanic community can basically ignore anything over about minus 1.8 because we don't have sea ice there. But this is just to let you know that over a fairly wide range of applied stresses and temperature, the creep component does a pretty decent job of capturing observed behavior. And the interesting thing here is I mentioned that if the dislocation density doesn't change much, then you don't get n equals 3 behavior. That's what you're seeing going on down at the low stresses in these two plots or high temperatures here. You'll have, as long as the dislocation density is increasing, you wind up with this fairly linear behavior, and then that falls off to something approaching linear behavior down at low stresses because you're not increasing the dislocation density very much. All right, so there's that. You can take these two relaxation processes and basically do this sort of incremental formulation. This is all spelled out in the paper, so I don't need to dwell on it. But basically, if you're going to take this approach, you're basically going to model the behavior over a bunch of time steps, and you need to integrate the inelastic components back to the beginning, more or less, of loading to capture the evolution in the inelastic components. But these are what give you that out of phase behavior. And then I just came up with this. Basically, it's the viscous component, but with the stress removed. That I did notice, I'll point that out. There was a mistake in the paper. The units on B0 are PA seconds, and the seconds got dropped off in the paper. Apologize for that. I didn't catch it until afterwards. But basically, temperature dependence is through this activation energy here, which is the well-established glide activation energy for basal dislocations. A couple quick notes on the orientation effects in the model. As I mentioned, if we go down in the sheet that's growing with an under ice current, after a C-axis horizontal microstructure is established, it refines into C-axis is still horizontal, but as you can see, the orientations of individual grains are starting to coalesce around a specific direction. It's sort of a top right to lower left diagonal here where you see down at depth. So that's at about 0.8 meters. But frankly, this is not that strong of an orientation. We've seen much stronger. But we want to account for that orientation change simply because once it develops, then our ice in the horizontal plane is no longer statistically isotropic. The resolved shear stress on the basal planes is going to be an increasingly strong function of the direction in which it's being loaded. So the way we handle that in the model is essentially calculating an average Schmid factor, which is basically a factor that takes the far field stress and determines the average resolved shear stress on the basal planes. We've done a lot of work there in validating this, and it's a very solid theoretically and both in terms of validating the basic concept of the shear stress on the basal planes is in fact what's driving the behavior, the inelastic behavior. But we've looked at this for quite a few specimens, and it's held up well. So one then takes the orientation data on how your individual basal planes are oriented. You calculate this, what I'm calling omega here, which is just this average Schmid factor. This is kind of tedious, but can be quantified if you take highly aligned cores and then or slabs of ice and take cores that are oriented at specific directions to that alignment. We've done quite a bit of this through the years on our field cores, and this works quite nicely, and you can see between the points here, which are actual experimental results, and the lines, which are the model predictions based on this orientation factor that we've calculated. You can see that there's an increasingly strong effect as the frequency decreases. So we're engaging more of these anelastic mechanisms here. We get more and more anelastic strain, and we see the anisotropy get quite a bit stronger for oriented ice when there's a lot of dislocation. So that's what omega does. You'll see that pop up. We've seen it in all the calculations so far. All right, so now I'm going to briefly talk about our experiments and these reloading experiments. And laboratory tests, we've had this methodology around for a long time, but basically it's uniaxial compression, although the samples clamped in a way that we could do reverse direct alternating tension and compression with this. We've applied a series of ramps, as I discussed before. And we saw this one earlier, but now we understand that as we're damaging the ice, we're in fact increasing the dislocation density. And we have this fairly substantial delayed strain that comes out after the unloading has started. Another case, this is faster, 10 MPa per second, a little over a second to get to our almost 12 MPa. In this case, a half a second phase lag between the peak stress and the peak and the resulting strain. This is just huge. I'll get back to this in a second, but this line I've drawn, basically the area under the curve here is the strain energy that is being released after the peak stress. So once the stress starts dropping, the area here represents the strain energy that's being dumped back out of the sample. By looking at the areas and doing an analysis we've talked about for these samples at various increasing peak stress levels, this is what I found. The dislocation density associated with those increasing hysteresis loop areas follows a stress squared relationship, which this again was another startling factor, because this is exactly the kind of behavior one gets at low stresses. I think the internal dislocation dynamics are quite different, but the fact that they're being produced according to this same stress dependence is, I think, remarkable, and it makes life a lot easier in terms of the modeling here. But as I said before, I don't have this relationship nailed down for fast loading, but this is a very encouraging observation that the dislocation density is increasing, not only as we see at lower stresses in ice, but this is a generally observed relationship for polycrystalline materials in general. So that's all very encouraging. So this is just a couple slides to show you. Again, the two things I've done here, other than plug in the temperature, and I feed the double, the load unload ramp into the program and use that incremental formulation to slightly improve the FET. I did decrease that peak width parameter, or increase it from 0.54 to 0.6. That tightens it up a little bit. Seemed to give a little better response, but not hugely. But the only thing I'm really changing here is the dislocation density. The model are the blue lines, and the orange are the experiments. And for these lower levels of damage and lower dislocation densities, I have no complaints over this FET. It actually almost looks a little suspect because it's so well. But I will say again, the only thing I'm doing here is taking all the parameter models or model parameters and putting in these dislocation densities that we determined from to get the anelastic response right. I'll also note, though, that I'm not attempting to monitor the viscous component. That's going to be pretty complicated, and I just didn't have time to really get into that. So I've primarily at the highest stress level here, just put in empirically a viscous component to match what we get in the experiments. The main thing, though, we're interested in is the anelastic component, because that's where the strain energy is. It gets dumped back out of the sample. The fit starts getting a bit shakier just before failure, but it's still reasonably credible that, I think we can go ahead and start improving this as time goes on. But I'm encouraged. And a quick note here, the amount of strain energy in collaborating with Heo at the TU Delft, he provided me with this estimate, a range of about 1 to almost 15 kilojoules per cycle of loading that would be required of a mechanism to sustain IIV. And sure enough, I ran some calculations on our experiments. I come up with a specific strain energy in this range here. When you then multiply that, or let me say, you need to determine a volume of ice that would produce the upper range of the values provided by Heo. And sure enough, it's something like 1.6 to 5.4 cubic meters of ice for the Nordströmgrund lighthouse would be required of damaged ice to provide enough energy here. And so that's pretty much what we have. So again, I'm very encouraged. A couple of quick points at the end. We did experiments with these ramp loading things on columnar freshwater ice. We saw nothing like what we saw with the granular ice, because that material is essentially more brittle than granular ice, and it would fail catastrophically before you could build up enough damage. Stone et al., there's some interesting work where they damaged ice under confinement, and Iliescu and Scholzen, this is all detailed in the paper, did biaxial confinement on columnar freshwater ice, and both found that they could impart quite a bit more damage than you can in uniaxial experiments. The strain energy levels come out to be of an order of magnitude that is pretty much what we see, and the anelastic strains as well. So that's all very encouraging. This is just an example. Just the cycle before failure with columnar freshwater ice, you really get these tiny little hysteresis loops, not much energy being absorbed. The very next cycle, it just ran up to failure, boo. And you just don't get the anelasticity out of that material that you do out of columnar or granular freshwater ice. And so I think, so experiments such as DEVS on columnar freshwater ice you just won't get the kind of inelasticity buildup before failure that you get in other ice types. So it's not surprising that he didn't see any energy input back into the structure in his scale model experiments. One quick observation is this business of the universal failure curve for ice, and some of the analyses out there lean heavily on this decreasing strength with increasing rate. I gotta say, just recently, I'm looking at a lot of the background data. This is not that well behaved of a process. If you look at, for example, the work from the Canadians on the damaged ice, this 40% damage at really high rates, you see a little bit of that. This is, the axes are flipped. This is, you'd have to flip the X and Y here. But you just don't see that fall off systematically. It's sort of there in a lot of data sets and sort of not there. So I sort of have some misgivings about that. Also, some of my own work from the late 80s. If you test fine grain material, you see that drop off, peak strength versus strain rate. But you just go up to 5 millimeter grain size, uniaxial compression, and that pretty much goes away. So in the strains at failure reflect this same business. The large grain samples just start their transition to brittle behavior much more gradually and at much lower strain rates than fine grain material. So it's just a really highly variable process. At any rate, I'm kind of a few minutes past where I hope to be. But my conclusions, you can kind of read through these, I think, and we can start the questions. But I will say thank you for your attention. It's been a real pleasure and very informative. It's kind of an unusual keynote to come up with new findings like this, but I felt that they were interesting enough to warrant your attention. So with that, I'll just say I think there are a few areas if someone were interested in pursuing primarily this mechanism. It's a pretty straightforward but not simple matter to basically flesh out this dislocation density relationship to stress, strain, and temperature, but at high rates, which I haven't done. That's really the piece that needs to be filled out before this could, you'd have complete confidence in going forward with this mechanism. But all the indications to this point, I think, are very encouraging. So with that, I'll end.
Thanks a lot, David. Thank you very much for excellent talk. And we have a few minutes for some questions. And I see Alexey Marchenko wanted to ask.
Yeah. Also, I can ask because it's very interesting that. So when you consider ice, so you mentioned today granular structure, then brine pockets and dislocations. So if you look for grain size, so it will be some millimeters, maybe centimeters. Brine pockets are much smaller. We cannot see them on thin sections. We see brine pockets in microscope, so then it probably some microns or smaller. And dislocations, they are on atomic scale. They are even much smaller.
Yes,
so then,
absolutely.
So then when we look on dislocation dynamics, we are in one type of scientific terminology. When we look for microscopic properties, ice rheology, we are on another side in continuum mechanics. So then this bridge from small scale to big scale is of course not evident. And then how it works actually, how how it is possible, because in general, in science, I usually, if you stay on some scale, you try to consider everything in this scale. But here we have good example when we can rise up small scale problems and they influence large scale problems. How do you understand that? Just please explain in simple way. So then different, specialists in different science would better have it in mind for future.
Yeah. Thanks, Alexei. I always love your perspective on these things. It's a great pleasure about working with you. Basically, let's consider a breakpoint between scale-dependent processes and scale-independent processes. So if you're talking, let's say, mode 1 fracture of sea ice, highly scale-dependent, and what you find at small scale can be sometimes connected to large scale, but it's not given, and you really need to do the large scale experiments to find out what's going on. It turns out that the constitutive behavior that my model captures is relatively scale independent. What we're seeing, and this is something I can continue to look at as I noodle my way into my dottage here. But we have experiments with the exact same loading methods, this cyclic loading approach, anywhere from, for sea ice, from let's say 10 centimeter diameter cores up to our largest in situ was 30 meters on a side slab of floating ice, 30 meters on a side. Most of our bread and butter experiments were 10 meters on a side and let's say 1.3 or 4 meters thick. And we have, I can do some fairly straightforward analysis of the phase lag that gets at this dislocation and elasticity over all these scales. And the model, oddly enough, as derived from the lab experiments, pretty much captures what we see at large scale on the floating ice. Mm-hmm. So the microscopic, the dislocation scale and elasticity doesn't go away simply because you have a large scale. It still operates as a function of the dislocation density that's there and the applied stress and the temperature. And I could, it was something I just didn't think I had time to get into here. But in terms of our experiments directly showing that the model works and that these dislocation processes, in fact, operate over many orders of magnitude of scale, I'm real confident in that.
Yeah, interesting. Yes, thank you. It's I think that's property of solid materials, because in water, for example, we have turbulence, so then molecular viscosity is not important.
Yeah, exactly.
Forget about that. But in solid, we cannot forget about small scale. It is always important.
Yep.
Yeah. Mm-hmm. Thank you.
Okay, thank you, David. We are now short on time and we have to switch to next points of our program. So we are very thankful for you for your presentation and for your lecture. And we keep possibility to send you the questions from other participants.
Yeah, absolutely. Yeah. Okay. Thank you so much. I appreciate it.
Yeah.
Thank you. Thank you. So with this, we finish the plenary lecture. Thanks again for Professor Cole, and we continue the program with the sessions. Okay. See you on the next sessions.
I guess that this is room number 1. We will have the session on mechanical conditions and ice strength. Yeah.
Yeah, I've just got in here. Can you hear me? Knut?
Yes, can you hear Richard? You're here and you will
Yes.
present the paper.
Yep.
And I see there's a Victor here. Is that Victor Epifanov? He wants to present your paper. Okay, he may be not hearing.
And I see the share screen as well, so that's
You can
good.
just try, Richard. You'll be last off, but just try it. Let's see if it works.
Oh, the share screen. Okay,
I see
I'll
that.
do that. Sure.
And I've seen Andre was here as well. Ian Jordan is not coming. Christian Skröder was also, yeah. That looks, now we see your screen.
Okay, so that's good. I'll stop the share then.
The first one should be, yeah, so Ian is not presenting a paper.
Yeah, that's too bad. Do you know if he submitted?
Oh, I think I wondered, and he just sent an abstract. I was surprised that it was put up in the program.
Yeah,
I
I
think
see.
it was paper even, so it gives us a little bit of time. I've seen someone called Christian Skröder on the previous session, so I guess he'll get back in again. And then Andre, I've also seen, and he's here somewhere, and Victor is here, and Richard is here. So then we have 4 out of 5 papers, but we'll give. We'll do it in sequence, but since Ian is not there, but there's no rush, we will have some time. No,
So you were thinking of just spreading the other papers out over the time of the session then?
try to keep. We can start a bit early. I don't want to shift too much because then if people are jumping between sessions,
Right, I see.
so we should try. But at least it does match if we start a bit late. That's.
The first presentation will be in time.
The first presentation might be a bit late because we're waiting for the presenter.
Oh, but if he sent, did he send?
I have heard nothing from none of them except for Ian, but I saw when Dave was talking and I was let into this room that the guy called Christian Skröder was present, and he is now he is the second author of the first paper.
Yeah.
Christian Schroeder is here now.
Can we try to share a screen so they will see that it works?
Okay, can you see my screen?
Yes, it looks very good.
Okay,
So
should I stop it? So let give everybody a chance to try it.
Yeah, Andre is not here yet, but I think we will just start. So welcome to this session on session number 11, mechanical conditions and ice strength. My name is Knut Høyland. I will be chairing this session. There are originally 5 papers, but only 4 will be presented. So Ian Jordan will not present paper. But then I give the word to Christian Skröder to present the first paper. So please introduce yourself and your co-authors and go ahead.
Yeah, hello everybody, and thanks for this digital opportunity to present our paper. The name of today's paper is Investigation of the Thermal Ice Pressure Loads by Laboratory Measurements. We've written the paper with 3 persons. I myself was a co-author of Patrick Buell together with Niels Reimer, and Patrick was doing most of the work on this part, but is actually not able to present today. So I will be in charge for the presenting part. I will give you a short overview of the content of today's presentation. So we will start with a little introduction and the experimental setup. We'll give you some insights in the experimental procedure, the observations done, as well as in the results, discussions, and conclusions, and also a small lookout about the findings we have computed during the testing. Generally, thermal ice pressure is a quite long phenomena. It happens when ice is, let's say, in a restricted area and it's heated up from relatively cold temperatures up to the melting point. Outside, it's relatively difficult to measure because it's a relatively seldom event and you never know exactly when it will happen. So our approach was if we can try to bring the nature and model this thermal ice pressure approach within our laboratory scales in a controlled environment, which can reduce the data acquisition time as well as instrumentation can be easier applied and also used for just a shorter time period of the measurements. Where does normally ice pressure occur in nature, thermal ice pressure? Mostly these effects occur in front of dams, port walls, non-moving ship hulls, offshore structure, but as well in water-filled tanks in case they freeze and the area is, of course, restricted in the tanks and they are heated up again. The tests were done in the Arctic Environmental Test Basin of the Hamburg Ship Model Basin. The overall facility has a water tank area of 30 meters long, 6 meters wide, and a 1.2 meter deep facility. We can regulate the air temperature up to -15 degrees to prepare the ice, but as well heat the room up again to up to plus 15 degrees. The cooling system can achieve an ice growth rate of about 2 millimeters an hour as a maximum. How was the experimental setup in our basin to measure the thermal ice pressure? And generally, we had some different panels and some different measuring solutions. So first of all, we had one smaller panel connected to one load scale you can see here. And then we had a bigger panel of a 2 meters beam connected to two load scales within the facility. And in addition, we had 3 tactile sensor mats to also derive the local pressures from the thermal ice pressure, as well as to detect possible, let's say, influences from the measurement setup itself compared to the measurements directly on the basin wall. Next to that, we had 3 temperature gauges on different locations. You can see the setup a bit more here in ice conditions on this slide. We had 3 temperature gauges, one a bit further away from the setup and 2 relatively close to the setup to measure the temperature profile over the ice thickness. Our target ice thickness during the tests was always 20 centimeters to have a fixed variable during the testing, and we varied, for example, the salinity of the ice. So you can, in the end, it's the whole test sub is a little bit part of extension of the basin sidewall with 2 different test plates to measure the pressure forces of the ice. During the freezing rate and before the testing, we always removed the ice behind the measurement setup so that there are no force chains in between the sidewalls and the measurement setup itself. How was the experimental procedure? So, of course, we first filled the basin with fresh water. In this case, we had a freezing process first to cool down the water and then to generate the ice sheet of 20 millimeters of about 8 days. And afterwards, we had a defreezing process of a bit more than, the tank itself was relatively warm after 7 hours. The ice itself needed a bit longer to heat through and until the forces could be measured during the measurement. After the initial setup of the freshwater tests, we put some salt into the basin itself to redo the whole procedure with salt water and to measure the effects of the differences from freshwater to salt water in case of the forces on the side walls. How were the general test conditions? So we used the more or less maximum or the coldest part of the basin or coldest temperature we can apply of about -15 degrees in the room. This is always, of course, much longer now here to the left-hand side, where the temperatures are at -15 degrees to generate the ice sheet. And afterwards, we opened the doors at both sides and put big ventilators on both sides to bring the air into the basin and reheat the whole room relatively quickly to generate a relatively quick heat up of the ice and then measure the responding forces of the thermal expansion of the ice. We could reach, let's say, 0 degrees in the room after about 3 hours after we activated the ventilators, and about after 10 to 13 hours, let's say the core temperature of the ice was in the region of 0 degrees, so at melting pot, and the maximum forces could be measured. If we now come to the test observations, first of all, a bit on the background of the temperature profiles during the measurements. So what you can see here on the top surface, after starting of the defreezing or the tempering phase, we of course had room temperature, so something about -15 degrees at the top layer, and then we had 3 discrete measuring points within the ice, or shortly below the ice. So the water temperature for fresh water was something about 0 degrees, and you can see the time scale up here from 0 to about 15 hours, and you can see how the warm-up phase came through the top layers of the ice further down until it went relatively straight from the top surface down to the water temperature. If we now switch here to the right-hand side to the responding temperature load profiles, you can see on the upper figure the temperature profile of the room. So it was about 6 degrees in the morning. We started the tempering process. So the temperature itself got up to about 0 degrees after something like 3 hours for the freshwater part now. And you can see on the force level, we removed some of the ice which was left behind the load scales or behind the measurement structure, something about 10 degrees, 10 o'clock. And afterwards, the ice got warmer and warmer. You can see it here on the left-hand side, so that after 4 or 5 hours, the ice also in the inner part went warmer, so the forces in the load sensors went up. So until I tried to make about 11 hours, we have reached the maximum force level due to the ice pressure on the sensors. So we measured about 10,000 newtons, so 10 kilonewtons on the big plate, and about 5 kilonewtons on the smaller test plate. If we now come to the observations compared to probably our initial expectations or ideas, we saw that the forces on the test plates had a factor of about 2, so 5 kilonewtons to about 10 kilonewtons, but the plate size factor is around 4. And the maximum applied forces or the maximum occurred forces could be measured after about 11 hours when the core temperature of the ice was in the region of melting temperature. We first of all then got back to our initial expectation, which loads we might have expected in which range, and compared that to different design load prediction models. And what we figured out that our, let's say, measured data is in the relatively low level or below the level of the prediction models. Of course, these are normally made for, let's say, thicker ice conditions in full scale, and also represent a design load where of course, the structure should not break or have any issues. So of course, these ones will be conservative. If we now come to discussions and ideas why probably the forces are a bit, let's say, different than we first expected and first thought about. Of course, in the end, what we measure is, let's say, we have solid ice before the whole structure. So there will be interactions, of course, with the side walls everywhere around the basin as well. Also with, of course, the solid walls, I would just say port and starboard of the test setup, but also with the panels protecting the rest of the measurement setup. So all the stiffness part will, let's say, be together, and you must think about how the pressure area curves or the pressure curves in the different areas might be. So we put up some hypothetical pressure distributions, how we can imagine that the pressure is distributed. So this will be also, let's say, a matter of further study and discussion, how the loads, what we now measured, can be interpreted, and also probably which kind of setups could be, let's say, optimized for future test conditions for thermal ice loads. Also now comparing the small plate with the bigger plate with a, let's say, area ratio of 4, of course, we come into the area where we also the pressure area curve takes some effects. So also these effects should be taken into account. To check also the stiffness of the overall setup, we measured the stiffness of the, you can see here, the support structure to the wall, the load scales, and then up to the outer panels. And we measured the displacement load variant. So, and what we let's say could conclude that definitely the load scale itself has a bit less stiffness compared to the surrounding part. So definitely the surrounding structure will take more forces compared to the a bit less stiff measurement device. So definitely if you already measure, you measure something different if there would be no measurements and just the walls, of course. What are the conclusions we could draw from the tests? So generally, the measurements confirmed that thermal ice loads decrease significantly with salinity. We didn't go into it too deeply in this short discussion here now, but from the tests we have done also in saltwater, the forces were, let's say, a level of 10 below compared to the freshwater findings. So definitely if you have seawater, we only took brackish water like the Baltic Sea ice conditions, the force levels are much lower compared to freshwater ice. The measured forces in this test setup were much smaller compared to theoretical calculated values. The pressure distribution in overall is, let's say, of course, also highly affected by the presence of the surrounding structure and its varying stiffness. So what is the outlook on the next steps we want to do? So actually we are in the phase of evaluating the local load sensors to draw a conclusion of the force levels directly on the sidewall compared to the a little bit less stiffer measurement devices. And also what we plan is to try to abstract the findings that we had a bit to, let's say, pressure distributions, probably like ship hulls or something different, where of course the areas which are stiffer, of course, take a much higher ice loads, for example, compared to areas where the hull bends a bit, so the force level generally is a bit lower. Generally you have to give some acknowledgement to the German Federal Ministry of Economic for funding the project in which part we were doing this work. And in the end, I have to say thank you for your attention. Thank you also for all the product authors and organizers for organizing this digital version in these times. And yeah, if there are any questions, I'm of course happy to answer them.
Thank you very much, Christian. If there are any questions from the guys in the Zoom meeting, you can take that while we're waiting for the chat to start working. So please.
I may ask if you like. Because, thank you for interesting presentation. And please tell again about the influence of salinity. How much loads reduced, and what was the salinity of ice?
So the load level was, let's say, in a factor of about the factor of 10 lower, and the salinity of the water itself was a Baltic water, so about Baltic sea ice conditions. So 1 promille of salt.
In ice or in water?
No, in water. I don't recall now what is the salinity in ice, but I can share with you, Alexei, if you like, if you have some further, let's say, interest on it.
Yeah, it would be of interest. But I think that salinity of ice was very small. And and it is interesting that you observe significant effect of salinity.
Yeah, we were also, let's say, really surprised that the force levels were so different.
But did you compare temperature profile change in time in fresh ice and in saline ice?
Yes, yes. We compared the temperature profiles. And
was it similar or different?
It was relatively similar. Of course, the salt water was the water temperature was a bit lower because of the salt in the ice, so the water could get a bit colder, but generally the temperature profiles were comparable.
Yeah, because of course it may relate to the different relaxation process, fast in saline ice. Or to different dynamics. I finished.
To comment here, Alex, say, and Christian, that the ice was quite young here. So when sea ice freezes, it takes a little bit of time before you get a solid matrix. Because we had some experiments in nature where we cut the base and have started freezing ice. And so perhaps this saline ice was a bit young to really get to develop a solid ice matrix. Because I'm also surprised by very small salinity and a very high effect. That's a bit strange. But, could be like that.
Of course, it was generally very fresh ice because we just prepared it, and after we had reached the thickness, we directly, let's say, more or less, melted again.
Yeah, so it means that the brine volume were distributed very well in small pockets all around, and didn't have time to form brine channels and more solid ice matrix in between, perhaps. But that's just
But you could, of course, to take out some small ice block and to measure in parallel forces and the thermal expansion of this ice block with free faces. So you would have some, understanding what is going on.
Yeah, I agree.
Yeah. But of course, it's very interesting direction. We also working with that. And,
so we are in the, we now, let's say, evaluated the first set of data, and now we are, let's say, more starting to the second set of data with this local load sensors to detect which local pressure distributions also probably over the ice thickness can be detected. So in which levels of the ice might be higher, let's say, force levels compared to other areas over the thickness. So this is one of the next research parts or the next evaluation parts we are looking for, as well as we are checking for the impact of the measurement setup itself on the results which is also, let's say, quite in our focus.
Yeah. In this year, we had 2 master students. They measured thermal stresses in sea ice and in fresh ice in 2 neighbor places. I think that it would be of interest to compare, of course.
Yeah, definitely. We are open. So it's a research project, so it's not secret. We can share some data.
Yeah. But
I've
we,
a
we
couple-
also observe quite big difference.
Richard, please.
Yeah, I have a couple of questions. The first was your pressures kilonewtons in kilonewtons per meter. It wasn't clear. I presume that's per meter width, and your numbers were smaller than what is in the standard and from other references, and it wasn't clear. Is that difference just due to the thickness of your ice, or I wasn't
No,
quite
we-
clear when you made that explanation?
So generally, we, let's say, we calculated based on the models to the ice thickness we had. But some of the models, let's say, they exclude the thickness of 20 centimeters. So most of them are more, let's say, up 40 centimeters or higher. So of course we were on some of the models on the really boundary conditions. So we were also discussing if, let's say, a lower thickness of just 20 centimeters to probably compare to half a meter or 1 meter thickness, which you might find in full scale conditions, will already have an influence on the force levels.
Another question just is with respect to your test setup. You have your on the side of the tank, you have your load panels, and then your I guess your frame extends a little bit further on either end. If you had extended that frame a considerable distance, do you think you would have gotten different pressure results? Because I guess there's a 3D effect in the freezing. If you'd extended those walls, you would essentially have got the same thing along down the tank.
Yes, we definitely had long discussions about all these effects. So what we mainly, let's say, if we would now redo it, the same experiment, we would try to make the, let's say, more or less all of the part, make it a measured area and don't have, let's say, intermediate areas, which are just, let's say, also taking the forces and maybe influencing the results. So if we would, let's say, redo the whole setup, we would try to measure as long as possible and probably just have vertical parts going back. So to, let's say, reduce the effects of, let's say, relatively close force chains directly into the wall, which might influence the results because, of course, the load scale and everything is always, it has some stiffness. So, and what we measure in the end, of course, we try to, let's say, block the ice as much as possible, because what we measure, of course, is the reduction in size increase of the ice. So if the stiffness is less and we have some relatively stiff surrounding areas, which we try to show here. So these parts here are mostly stiffer than the load scale part. Then of course the forces we get measured are lower compared to the forces if, let's say, the whole part here would be one measured test section.
Thanks.
So I have a comment on your on the measured loads. So you only had 15 degrees of increase. So this in ISO and many papers, they often find the worst case. So then they measured 25-30 degrees increase in a day. So that it could be that if you manage to increase 25 degrees in the 15, you will get higher forces.
Yes, that's
an explanation. I mean, you don't really have the worst case with only 15 degrees of increase.
I agree. What we also found is that most of the, let's say, most of the forces, let's say, which occurred are in the last degree. So I agree. It might be, let's say a reason, but from the findings or from the, let's say, conclusions now from the temperature change to the forces, what we could see that the highest force level or the highest increase was, let's say, in the last 2 or 3 degrees, from -3 probably to almost 0. There was the biggest, let's say, I think force expansion level or something like that, you can call it.
That could be because when you hit top surface level of ice, it wants to expand, but bottom level resist for that. So then effect is strongest when temperature gradient is smallest. So then because you have floating ice, if it would be just all ice with the same temperature, it would be different.
Correct.
So we measured full scale, quite high stresses, 200 megapascal, 200 kilopascal in floating sea ice. But of course, there are different time scales. There's one time scale in the heat penetration, and there's one time scale in the relaxation of the ice. And these 2 time scales, in a way, they compete. In addition to Alexei's point about this, it's three-dimensional features. So it's
Yeah, you could.
the problem.
I am sure that, of course, temperature in the whole room was not similar, and the heat transfer was different. So therefore, of course, could be some 3D effect. And if you would use this infrared camera, you could see maybe how this surface temperature changed over the tank surface. Maybe it could tell something. We measure it up to 600 kilopascal in Cap Amsterdam. Confined ice, but Knut, you told about natural stresses in.
Yeah, we measured inside the ice, not on the structure. So that's
Yeah.
how are the boundary conditions towards the beach and this trim tank? Was it open towards the trim tank, or was it sliding on the beach? And what were the boundary conditions in the long direction?
In the long direction, so if we go through it, so it was relatively in the middle of the basin. So it was something like here, the test section. So the distances to the trim as well to the melting pit were relatively long. So we would assume that, let's say, the side effects from these sides here are relatively low, but more, of course, compared to the forces which are, let's say, directly interacting to the wall, because of course you have the whole ice which forms, let's say, one, let's say, force chain. So of course also some of the forces are directly going to the wall, which are, let's say, most probably the stiffest part of the basin.
Yeah, but of course ice can expand along the tank, and it also will reduce the stresses.
Yeah, that was my point, because
Yeah,
the
exactly.
expansion is in all directions, or both horizontal directions. So it's not obvious. So you should get higher stresses in one direction if you can find the other direction, as far as I can understand, because or else.
Yeah, because it is viscous. So viscosity of ice is important for that.
Oh, it's very interesting experiments. There are no questions I can see from the chat. We still have a few more minutes before we leave Andrei to talk. So if there are more questions, be interesting to follow this. We also try to work with this, and I'm also comment that on fjords and rivers, this might also be a problem, at least in fjord crossings in Norway, the bridges and then the thermal expansion is one of the issues.
Yeah, also in German waterways and German bridges, we have this issue. So we also have this, of course, icebreakers on the rivers to really protect the barriers and the bridges, let's say, especially shortly before the, let's say, the warming season, so that, there were no, let's say, no damages. But also for us, it's a, let's say, a relatively new topic we were looking in. So we are more normally addicted to ship hull testing and all this part. So more getting into the ice mechanics and also this thermal effects really is an interesting part for us. So it's a nice and good research topic.
Oh, very good, very good.
I had a request from my friend in Canada. He has a cottage on the lake and small pier for a small boat. And the question was how to survive, how to make pier that it will survive over winter time. What to do, because it is usually damaged by probably thermal expansion of ice. So then this problem, you know, which is important for many users.
You should
Customers.
just have a floating pier and take it up in the autumn, put it down in the spring.
Yeah.
No, it is not floating. It is on the lake, but small. Yeah.
Okay, thank you very much, Christian. Interesting
Yes.
work. I'm looking forward to hear more about thermal expansion and these kind of stresses from HSA. And then, André, I guess you're ready. You can try to start sharing your screen. Okay, well, I see that Steve Bruno from Canada has a couple of comments here. Thousands of Canadians have dock problems. Question being asked now. And then Anne says, have you looked at Sanderson consideration about thermal penetration depth? Thicker ice doesn't mean higher loads due to thermal penetration with depth. You might answer, Christian, if you looked at that before we leave André to talk.
Sorry, I did not totally get it. I tried to look it up.
Okay, so Steve was just saying that this is a challenge in Canada, but Anne asks about the ice thickness, the effect of ice thickness. Because I mean, it penetrates, so the ice thickness, it doesn't scale with ice thickness. So did you look at the ice thickness effect, so the penetration of heat and
No, not so far, but definitely that was one of the discussions point we always had, how big the effect of our relatively thin ice thickness we had in the basin now affects to the overall force levels. So we have not looked into the thickness point of view, but it's definitely a very good point, which should be further analyzed if there is a thermal ice, let's say, pressure relation to the ice thickness. But they mean that thicker ice doesn't mean higher loads. I might not comment on that today because so far we are not at the current stage.
Yeah. Okay, then André Murza, please, from Dartmouth. Introduce yourself and your co-authors. And
hello, everyone. My name is Andrew Murza, and my co-authors are Arto Poliari from Aalto, Finland, and Aron Chilson and Carl Renshaw from Dartmouth College. And the topic of today's talk is the flexural strengths of bonded ice. Okay. So why do we want to look at freeze bonds? Because freeze bonds are common features in Arctic and Antarctic regions. We do often get the ice floor breaks and then refreezes back, or sometimes we have a lot of individual blocks get together. And in order to understand the strengths of these features, we need to look deeper into the strengths of these freeze bonds. And there were some recent studies by Poliari and Tukuri that showed that the individual freeze bonds within the deforming rubble rather fail through tension and not through shear. And a lot of work was done previously on where freeze bonds were studied on a combined compressive and shear strengths and shear stresses. And the goal for this work was to look at freeze bonds under tension. So for this, we grew freshwater ice, freshwater columnar S2 ice, and as you can see, vertical and horizontal microstructure of the ice that we used as a parent material. And the C-axis orientation confirmed that we indeed grow S2 ice. So we had a block of ice that we grow, and the columns that were oriented, in this case, vertically. The grain size was about 3 to 8 millimeters. And we were preparing ice plates as you see on this image in blue accordingly. So how we prepare the test? So first we milled the specimen, the ice plate. Then we cut it with the bend saw, and in most of the test cases we milled this cut surface such that we receive 2 parts of this ice plate, and these parts would be later brought together in contact. So then these surfaces that are supposed to be brought into contact were sprayed with a fine mist of temperature 2 centigrade, and the salinity was varied from 0, meaning the fresh spray, to up to 35 ppt, parts per thousand. So then quickly after spraying, the surfaces were brought together, and here on the left image you can see the schematics. So these white are these 2 pieces of ice brought together, and we also did inject some little bit of extra water with a syringe just to ensure that the surface of the bond is fully wet, and if there was any extra water, we would just wipe it out. So we would add some compression. So using this mechanism, as you can see, we would use 2 plastic bars and springs. And so we could vary the pressure, but we did, for all the tests, we used the pressure 4 kilopascals, which is the maximum hydrostatic pressure within submerged 10-meter thick ice rubble mass. And the orange thing was made, the whole setup was made from, the orange was acrylic, such because it has a low heat conductivity. So we wanted to ensure that all the heat flux is occurring along perpendicular to the bond, along the long axis of the sample. And one important thing to mention, that these experiments were done in air, not submerged in the water, but air. And on the right, you can see the image, how it was done. So then after freezing, we could see this freeze bond in the sample. And then we would place the specimen with the freeze bond into the 4-point bending apparatus, as you can see here. And well, one may ask the reason why we wanted to simulate this bond vertically. The reason is that ice flows sometimes break vertically, making the vertical fracture, and then later they refrozen. And these ice flows are subject to the wave ocean, to the cyclic, and so we try to simulate this simple situation. So this 4-point bending apparatus would allow us to bend our specimen in the following way, as you can see. So initially we used the freshwater bond. So we sprayed with the freshwater fine mist, then brought these 2 parts together and waited for the time ranging from about half an hour to up to 25 hours. And then after that, we tried to measure the strengths. And so we did this at 2 temperatures, at -10 Celsius and -3 Celsius. And these 2 vertical dotted lines, they show basically the upper and lower band for their measured strengths for the intact ice. The ice didn't have a bond, just to see where our new data points fit in this. And as we see, the all data fit within this range pretty nicely. With the 1 point slightly below, there could be some probably issues with the alignment, because in 4-point bending, it's the sample is very sensitive to them. And so the conclusion from here we can make such that even half an hour is enough for the freeze bond to reach the full strength, sort of. So the freezing occurs in less than half an hour. And one important thing to know, that in all of these cases, the failure occurred outside the bond. On this image, you can see that the freeze bond was on the left, although the failure occurred on the right. So it indicates that in all cases, the bond was probably stronger than the parent material. And the reason for this is that when we create this bond, we spray with a fine mist, and probably the grain size is very, very small within the bond. And as we know, the smaller the grain size, the greater the strength of the material. So that's possible reason. So the next one, we investigated the saline bond. So we used still the freshwater parent ice, and we sprayed with a saline mist and followed exactly the same procedure. And we used salinity of 12 ppt at -3 Celsius, and we also used salinity 35 ppt at -10 Celsius. And you can see the results in red and black correspondingly. From this, you can see that unlike with the freshwater, here with the saline bond, the strength saturates a bit slower. So it takes somewhere from maybe 6 to 15 hours, roughly, to saturate. And after it saturates, it just stays constant. So important to mention about the types of failures we're receiving. So in those freshwater ice bonds, as I showed earlier, the failure would always occur outside of the bond. In the case of saline bonds, the failure would, most of the cases, go right along the bond, and then on image B, you can see how it looks like. However, sometimes it would still initiate, the failure would still initiate along the bond, but then slightly deviate, as you can see on the image A. And then on image C, you can see the bottom part of the sample, you can see that the fracture was along the bond. You see kind of rough surface. And then on the upper part, we can see the clear sort of new ice, newly formed fracture in the new ice, not along the bond. And so for all my results, in case if the failure occurred outside the bond, I would use the triangles, different symbols. But in most saline ice samples, as I mentioned, the failure was along the bond. So on this, here I want to show the results, how the flexural strengths, and I want to emphasize that we're now investigating saturated flexural strengths. So we look for the strengths after something like 15 hours or more, usually around 24 hours, as a function of salinity. So we did use different salinity sprays to make the bond. And then our points are in black. And then here on the left, you can see a few blue points. Triangles, these are the cases where the salinity was 0. It was a freshwater bond, and the failure occurred outside the bond. And for comparison, we provide data from Timko Bryan, where they had over 2,000 where they summarized over 2,000 tests. And interestingly, that the pattern, the trend is very similar. The only thing is that our data are slightly higher. We have a greater flexural strength. And I explained earlier that probably it's because of the grain size difference. So the next set of data was obtained at the constant salinity, 20 ppt, was for all the tests. And we arranged the temperature of freezing, the air temperature and ice temperature during which the freezing occurred. And again, it's a saturated flexural strength. And so you see, as we lower the temperature, the strength is increasing as we would expect. And at -25 Celsius, most of the points, most of the samples, in most of the samples, failure occurred outside of the bond, indicated that the bond is already at least as strong as the parent material and probably stronger. So the conclusion of this work is that the freshwater bond formed in air, so the strength exceeds the strength of the current S2 ice in less than half an hour upon freezing. In the case of sailing bonds, it takes about 6 to 12, maybe 15 hours to freeze to saturate the strength. And then as we increase the salinity or we increase the temperature, the bond strength is getting lower. The relationship between the bond strength and salinity that we obtained is exponential and similar to the one suggested by Timko and O'Brien. And no freezing occurred once the salinity of the freshwater, salinity of the water that we used to make the bond reached about 25 ppt. So at -3 Celsius. So we try to use 25 and 30 ppt, and the bond just never occurred. These two parts would never bond together. Thank you for the attention. I'll be happy to answer any questions if there are.
Thank you very much. It was an interesting presentation, and then we take questions. I'll try to keep an eye on the chat as well and read the questions there. So please. Yeah, well, I can. Well, I think it's also very interesting experimental work. So your data lies a bit about.
Mikko, can you repeat, please?
Have you heard anything about the speakers or the ones who should present in this session? I haven't received any emails. Actually, I just found the email regarding this session today morning.
Mikko, do you hear me? Because now you're in a session here, so there's something wrong with the. Okay, let's forget about that. Yeah, so Andrei, your curve lies above Timko and O'Brien, but it could be because you have mostly fresh. Yeah, this one. But when it didn't fail, when partly fell outside the bone, it became stronger. So that the fact that you don't have saline ice all over just in this small bond could explain that it gets stronger. But I don't know. That's. Do you have any comment on that?
Well, so for most sailing bonds, the failure was along the bond.
Yeah.
So mostly the failures outside were the freshwater ice. And as I said, we indeed had the green size very small.
Everyone speakers here and ready to enter.
So.
Yeah. Okay. Yeah. So that's a.
If you have any other ideas for what this ranks could be, I'll be happy to.
Yeah. No, it's. It could also be because your experiments are well prepared, so they are more uniform, more stronger, and things like that.
Oh yeah.
And you also force, if you have one weak link, you force the crack to grow there, even if it wants to grow somewhere else. But I don't know. There was a question from Anne here. Let's see. Let me read it up. It's in the chat. From Anne Barker, how do you expect your results to change had they been submerged?
Well, there's a number of research done on the ice samples that are submerged, and people were discussing different stages of this strength evolution, where the bond not necessarily always goes up, but there's stages when it's weakens. And for sure, we would not expect the strengthening to be fast, like as we said, like in half an hour or a few hours. Second, we would never, I doubt that we would ever get to these high strength levels, like to the, we got this freeze bond stronger than the parent materials. I think that's the main kind of difference, what I would point out at this point.
May I ask a question?
Yeah.
It's on YouTube, so welcome to the 2021.
It's a bit strange. Organizers, we seem to have two sessions in the same
room.
In the same room.
The session, and this session is about mechanical conditions and ice.
But
Should I say
something, Mikko isn't here at the point, must be.
Riikka Matala.
I can only ask the organizers to try to fix it. It seems that there's
Yeah,
something wrong here.
let me-
Grass ice material property.
Anyway, okay, André, we have another question from C. Bruno. Are there implications here for de-icing ships, vessels
Good
in
morning.
freezing spray situations?
My name is Riikka Matala, and I'm very happy about this opportunity. to
Well, we
present
didn't look in the
online
de-icing
ice
problem.
We're
going on
actually
in the world.
having
Can you hear
a replay of this morning's
comment?
session on top of our
Yes, we can
session.
hear you.
Okay, very good. Okay, can you see my slides? No, probably not.
But Alexei is
I
trying
think
to
you
get
are
a hold of
seeing
the
them.
organizers, so we just have to. But so André, about the de-icing of vessels, do you have any comment on
sorry.
that? Steve asks.
Well, I never worked with the de-ice, and I'm not sure if I can make a
Okay,
proper comment on that,
do something.
because it's a little bit, I think
now
it's
I
a bit,
understand.
although related, but not directly. The conclusion cannot be directly made from our study, I think. Yeah,
I
sorry about that.
say that the host is displayed. My
Alexei, did you want to ask something?
Can we
Yeah,
go
I
to
wanted to ask, I wanted to raise up question. It was discussed in book of Sanderson, because when we measure flexural strengths, we may, from one side, we may
Can you
tell about initiation of crack at the surface, or we may tell about growth of cracks which were created before the experiment. So, and maybe that is the case for this situation. We may some surface damage in
Can you see it
in
now?
a freeze bond, and then the surface of ice could influence results. So that that is my point. And if you look for that or not.
Let's start over.
Well, it's a good question, and
Okay.
what we were asking ourselves was that whether the failure occurs within the bond or failure occurs probably
Okay,
between the
let's
bond
start
and the
over.
ice,
My name is Riikka.
because there could be
I'm
some
presenting me.
some
I am
defect there.
Hanyan Gong
and
study.
we're not able to identify
I
the
focus
the location of the initiation, unfortunately.
channel model.
Yeah, I understand. But also it could
Our
ice
presentation
could be broken
using
not inside the bond because it was some initial crack outside.
grass ice
And
practice.
you didn't see
Why
that.
you-
Well, could it be possible?
You mean far away outside the bond, like in the those fresh water where the bond was away from the.
Yeah, just occasionally it may happen.
I don't think so, because we grew this ice in the laboratory, and the ice was like nearly perfect. There was no defect, no visual defects.
And how did you apply force?
Well, it was using a 4-point bending, as I showed previously. It was so we would.
So then you apply force in the center.
Yeah, in these two middle rollers.
Oh, you okay? You okay? I
Not
see.
the center of the beam, but the middle rollers. Or
Yeah.
in this image, these.
So it's a 4-point bending. Not
Yeah, it's 4-point
Yeah,
bending.
yeah. But if you would not have this freeze bond, it would be perfect ice. Did you always observe that crack was in the middle?
Yes, always.
Mhm.
I would say in 98% of the situation, 99, the crack was always in the middle section, and 1 out of 100 maybe under the roller.
But
Yeah.
never to the side of the middle. So it means the moment was biggest in the middle, so you don't have a proper sort of flat moment in the middle sections.
Yeah,
Good
the
point.
moment is distributed, I think. Yeah.
Okay, but I think we need to move to the next presentation. So thank you very much, André. Another interesting presentation. And Victor, are you ready? Try to share your screen. Victor Yepifanov. So Victor, you are logged in. Are you ready to present? It's a bit strange because he was logged in all of the time, but you know this guy, Alexei?
Yeah, I know him. He's from Institute of Problem and Mechanics.
No,
Yeah.
I guess we just wait a couple of minutes to see if he. But I don't want to start you too early, Richard, in case somebody moves from the other session to listen to you. So we wait a bit before.
40 minutes would be fine, though.
40. We could also swap so that you'd go on now with the
Yeah,
program, but anyway, I think it's better because then we avoid waiting. So if you just start, Richard, and then we'll see if Victor can do the last presentation.
Yeah, maybe I will ask. Yeah.
Can you see my shared screen okay?
Yes. So
Good.
please go ahead, Richard.
All right. Well, I've been a consultant for the last 30 years and the last almost 20 years working on my own. Greg is also a consultant, and I've worked with him on many research projects and consulting projects over the last 30 years. And Greg is now adjunct professor at Carleton University in geography and environmental studies. And they're involved in a number of sea ice and glacial ice projects, mostly in the Canadian Arctic. This, just as an introduction to this paper, is Young's modulus is used in many calculations involving sloping structure loads in the 19906 standard. The breaking component of load in Crozale's formulation is proportional to Young's modulus to the minus 0.3. And what that means is that for a decreased Young's modulus, you actually get an increased load. And so any reduction in Young's modulus or a reduced effective modulus gives you an increased load. In the ice-breaking component for ship resistance, the load is proportional to e to the minus 0.5, so it's a little bit stronger effect. In a bearing capacity equation, also in the ISO standard, it's E as a function of the, it's the bearing capacity is a function of log E. And so the effective modulus in many practical problems in nature can be significantly less than the elastic value. And there are a number of reasons for that, and I'll deal with them in the paper. But the elastic value, using the elastic value, can yield inaccurate results. And it can often be difficult to estimate an effective modulus based on experiments. And we've used a numerical approach to estimate effective modulus in this paper. And so what we've tried to do is represent viscoelastics. And in this paper, we deal with freshwater ice, but the techniques are applicable to sea ice as well. And the approach we've taken is we've looked at a representation of 3D mechanical behavior, including delayed elasticity, accounting for example, isotropy in the plane in the horizontal plane for S2 ice because of randomly oriented crystals, and also anisotropic effects. We could deal with a fully 3D anisotropic medium. And we've implemented this in a 2D finite element solution, and we calculate time-dependent effective modulus in bending. Just as a background, Greg has a lot of experience with looking at cross sections through ice, and on the left, I've shown a couple of the sections he's taken where you can see different amounts of entrained air within the ice. Both of these are sea ice samples. You can see clear ice at the bottom of the Northumberland Strait sample and larger grains from slower ice growth. In the Sakhalin example, there's a considerable amount of brash and smaller ice pieces underneath. One typically gets a bit of snow ice on top, but over the depth of the ice, the effect is relatively small. So we focused on on S2 ice in this paper. I've shown here on the right a temperature profile that Michelle Johnson took from some Sachs Harbor experiments. And you can see that it starts at the water temperature of -2, the bottom surface, and the profile is approximately linear through the depth. In the model we've worked with, we deal with viscoelastic behavior, and there are three main components. There's an instantaneous elastic component, which is slightly anisotropic. It's temperature dependent, and for isotropic ice, that can be represented. Any volume changes under loading can be represented using Young's modulus and Poisson's ratio. Whereas what we do is for S2 ice, we deal with 4 different elastic constants. The delayed elastic part is the main contributor to primary creep, and that's an important contributor to the results in this paper. The assumptions, it's a standard temperature dependency for creep. The behavior is anisotropic, and we rely on, as documented in the paper, the Sinha's work and his student, and also the effective stress measure that Shyam Sunder used a few years ago. We also include a viscous component, which is a power law for secondary creep. But for the short times we look at in this paper, it's not relevant. The setup that we've used is the flexure of a freshwater S2 ice beam. And that beam is 1 meter thick and 10 meters long. In width, we've considered a unit width, and we look at both plane stress, where it's unrestrained in the width, or plane strain conditions, where it's restrained in the width. And we've got S2 ice through the thickness. We're looking at a temperature profile of -20 at the top surface, going down to 0 degrees. For this simply supported beam, if loaded at the center, either using a force or applying a displacement, the beam equation applies, and that's the elastic beam equation. If one inverts that equation and looks at E as a function of your applied load and your displacement, that is what we use to get in this paper to get effective moduli. So we model the whole ice beam, the viscoelastic ice beam, and we look at the development of load and displacement at that point. The stiffness of the beam is effectively EI, where I is the moment of inertia of the beam. We also, in some of the later slides, I've looked at top surface stresses and strains for an element at the top surface and at the bottom surface as well, just for comparison with the results derived from the beam equation. So this next slide, I've shown a finite element solution for flexure of an ice beam. So I've got an applied constant load of 100 kilonewtons per meter width. It's a plane stress condition, so it's unrestrained in the other dimension. And what I've shown here are principal stresses in a vertical section of the beam. And the solution, I've shown a solution after 10 seconds. And the reason why I've shown 10 seconds is because that's approximately the time scale for if you're flexing, if you're bending an ice sheet up against a sloping structure, or for flexure under wave action in the ocean. And in this figure, if you look carefully at the bottom, I've actually shown displacements at all the nodes in the model, and those are little blue arrows. And the maximum displacement is at the center of the beam under the applied load. There are compressive stresses at the top of the beam and at the reactions on the side. So those are the local effects as a result of the applied loads. We've got tensile stresses in the bottom part of the beam, and I'd emphasize that because of the temperature dependence in both elasticity and in creep, or primary creep and secondary creep, is that it's not completely symmetric top and bottom. If you had an elastic beam, it would be symmetric. Again, this is it's a figure that I've shown in the paper. So when you get the paper, you'll see this. And what I've done is for that same experiment, or the same numerical experiment shown in the last slide, I've got a constant load of 100 kilonewtons per meter in plane stress. And what I've done is I've called it the effective stiffness, but that's the effective Young's modulus. And it starts off at the elastic value at time 0, and then decreases over time. And I've plotted three different ones. I've got the based on the forces and force and displacements at the center of the under the applied load from the beam equation, and you can see that it decreases from a little over 9 GPa to about 6.5 GPa after 10 seconds. And so that's based on published models for freshwater ice. So it's quite significant over that time. And you can see that at the top and bottom surfaces of the beam, they bracket at the bottom surface, which is warmer. You can see that the effective stiffness is less, and that the effective stiffness at the top of the beam is a little bit greater, and that the effective modulus for the beam is a little bit closer to the bottom, to the behavior on the bottom surface. Go on to the next one. And here I've got a constant loading rate of Oh, I just got out of that accidentally. A constant loading rate, and so I'm ramping up over of 10 kilonewtons per meter, and so I'm ramping up over that stress or that load over 10 seconds. So at the end of the 10 seconds, it's actually this same applied load. And you can see in the blue, the top and bottom in the beam equation, I've used the total force and the total displacement, or the total stress and the total strain over that time period. And you can see at the end of 10 seconds that the result is slightly more. So the effective Young's modulus after 10 seconds is greater. So it's about 7.2 there as opposed to 6.5. And the reason for that is because there's more displacement as a result of viscoelasticity, because in the previous plot I showed, because the load is on for the entire 10 seconds. So here we're ramping up the load. So effectively, we've had less load on the beam over that 10 seconds. I've also plotted incrementally from the beam equation a delta F and delta displacement, and also the delta sigma and delta stress and delta strain. So the incremental values of stress and strain. And you can see that in that case, it's actually less. So you have a slightly lower effective modulus when considering incremental values. And that's basically because you're starting from a lower point. The little blips in the curves there on the left. That's I should have chosen my elements. One, they're under the effect of the applied load. So there are a couple of processes going on. So I should have moved them over a little bit away from the central applied load. This table is shown. The next table is shown in the paper as well, and I've run 7 finite element runs here, and I've got different applied loads at the midpoint, and I've also got applied displacements at the midpoint. I've got a constant load application in the 3 first ones, and then I've ramped them up linearly in the lower ones. I've also looked at there are 2 different runs which were a constant load, and one was run for plane stress and the other for plane strain. And I've plotted the effective modulus over the elastic or Young's modulus after 10 seconds. And you can see that the plane strain value is greater. So effectively, by restraining the beam, the viscoelastic behavior gives a slightly stiffer result. That's kind of interesting. And in most situations that one would get are somewhere between plane stress and plane strain. So applying the resistance restraining the beam makes the beam effectively stiffer. Here, what I've done is I've compared the constant to ramp values, and this is essentially what I showed in the previous 2 plots, and so that you can see in the difference in the relative values compared to the elastic values at the end of the 10 seconds. I've also, you pose the question, okay, well, if you, rather than applying a maximum value after 10 seconds, if I stretched out the time over which that load was applied and I stretched it out to 100 seconds, you can see that the effective modulus based on total stress and total strain decreases quite significantly over that 100 seconds. If you spread it over 1,000 seconds, it'd be even less. One thing of note, just looking at the results, all the results, the effective over elastic modulus for all the 4 ramped values, whether it's ramping a load up or a displacement up, you can see that the ratio of effective to actual Young's moduli are essentially the same. And basically that means is that the delayed elasticity is responding quite quickly and quicker than the time over which that load is ramped up. There's a lot in this, and there's a bit more discussion in the actual paper. So just to finish up here, our next step in this work is we intend to publish the work in a refereed journal. Just more details of the model, because there isn't much space in the POAC conference proceeding. We've looked at sea ice in a similar way, and effective moduli tend to be less, because the ones we've shown for freshwater ice in these curves tend to be high, tend to be a little bit higher than what one sees for sea ice. And particularly with sea ice, it's really important to look at the actual structure that you have, and to use experiments and really to validate the coefficients that we use, the creep coefficients, to observe values. We've also looked at isotropic ice or glacier ice, and it's just an isotropic version of what we've shown in this paper. Other problems that we've looked at, we did write a cold regions paper where we looked at stresses in landfast ice, both due to wind stress over the surface and tidal jacking from shore. We've done some preliminary work, unpublished work, on the iceberg calving problem. And what that is, it's if you have an overhanging beam of ice undergoing wave erosion, one has it's a continuous process where you have a temperature gradient within the ice. And we found that compared to most of the work that's being done on the iceberg calving problem uses an elastic assumption for ice behavior. And so we found that there is a viscoelastic effect, and that influences the way this behaves, and that influences the maximum stresses that you actually see at the base of the overhang. We've looked at load sharing for grounded features in a stationary ice cover in the Caspian Sea. And certainly for any work with waves in ice, accounting for the viscoelastic effect can be quite important. The last slide is just a number of pieces of Canadian art that have used an iceberg theme, but some are some quite famous Canadian artists. There's a stamp that has an iceberg in the background, but it's kind of fun to see how it's been represented. That's all I really wanted to say for this this presentation. And
thank you very much, Richard. We have some questions. By the way, I got a link and a film that I will show afterwards for Victor's presentation, and that seems to last about 12 minutes. So then we have time for a few questions, because Victor is somewhere else; he cannot talk. So, a question for Richard, please.
Yeah, can I ask? Because I have
yes, you can ask.
one comment. Because you mentioned about difference of elastic modulus for plane strain and plane stress. In plane strain situation, So we use rigidity. So then in reality, we use not Young modulus, but Young modulus divided on 1 minus squared Poisson ratio. So if we use this value, so then it will be bigger than Young modulus. And I think that it could be effect. You did mention about Poisson ratio, but it is the case because 1 minus squared Poisson ratio, that is about 0.9, or could be 0.8, 0.9. So then you will get this effect. So then it may relate not only to viscosity, but also to the Poisson ratio effect.
Well, it's the model actually includes both elasticity and delayed elasticity. Elasticity, if in the plane strain condition, it works as you suggest. With viscosity, it's and delayed elasticity. It's essentially it's conserving volume, and so you're actually trying to the ice is having to be pushed out the top and bottom surfaces. It's not allowed to expand to the side, and in this work, the delayed elasticity is multiple times the elastic deformation, and so I think that's the most significant contributor to that effect. Or that's my impression. I could check it, but
you calculated like effective elastic modulus using the curvature.
Yeah, well, it's the effective elastic modulus that's based on the beam equation. It's just the relationship between deflection and force at the center of the beam.
Beam equation is derived with assumption that there are no lateral stresses. So the lateral faces of the beam are free from stresses. And when you tell about plane strains, so then it means you keep beam faces like parallel.
Yeah.
So that is like a part of plate. So then equation of beam depend on elastic modulus. Equation of plate depend on rigidity. So that is ratio of elastic modulus divided on 1 minus second power of Poisson ratio. And it make a difference because you are talking how to measure elastic modulus from the shape of the beam. But it can relate also to the effect of beam deformations in transversal direction. So that is effect of Poisson ratio. So that's what.
So you're suggesting I should have used a plane strain beam equation to show that. That's in that case.
You should get different results.
Yeah.
My point, but the difference can be explained not only by viscosity, but also by effect of beam deformations in transversal direction. So that is.
I don't see any questions in the chat, so if there are some of the others inside the Zoom room want to talk, then but it's just interesting to note that there are now, for the first time for a long while, a lot of presentations including the time dependency of ice. So I hope that we now start understanding more and we'll be able to use this time dependency because we know it exists, but we've never used it really for any practical purposes when it comes to making calculating ice loads or bearing capacity. So I think that is a good that is interesting to see.
Yeah, I agree absolutely. And Richard, you today I made presentation and with very similar conclusions about experimental properties. So it was too early for you to to follow that, but yeah, I can send you the file.
But this, I guess the way that the model is set up is it's basically a 3D model
Yeah, yeah.
with all these components of ice behavior. And then one just converts those equations to a plane strain or plane stress condition and
also
models it. And the finite element model, like it runs and like runs quickly. It's just an explicit model. It's really simple to run and runs quite quickly.
And also, I completely agree with you that there is difference between ice properties in vertical and horizontal direction, both in viscous and elastic properties. So then that is important to use elastic modulus Poisson ratio in horizontal, measure it in horizontal directions for the bending problems.
No.
I think that we, to get the coffee break, we should start, we should look at the last presentation. I guess you all see it now. It is made by Viktor Epifanov and his colleague K.E. Zazozanov, and it is a film they sent me, so we'll just play this. But they are unfortunately not in a situation where they can answer questions afterwards. So play this, and then we'll have coffee break. But okay, so let's go.
Duration and evolution of model ice texture peculiarities by two authors, Viktor Pavlovich Epifanov from Ishlinsky Institute for Problem and Mechanics in Moscow and Kirill Evgenievich Sazonov from Krylov State Research Center in St. Petersburg. Authors would like to bring their excuses that they could neither present it nor participate in talks. In case of questions, authors would appreciate to receive them in either Russian or English via email, as on the last slide. This presentation is about experimental data concerning formation, futures, and evolution of the texture of the model ice. Prior papers mentioned on this slide will be providing more information when required. This slide gives more details about two experimental locations. The first, Krylov Research Center, is unique due to its size of 800 square meters and all available facilities. It should be mentioned that in both locations, all measurements were performed directly. On this slide, hardness as a primary characteristic is discussed as a basis for the used method. Here you can see three tips originally used for the measurement: double-edged, cross-shaped, and the blunt. Here you can see measured dependencies from the tips type at two different measurement points. What's interesting, that different penetration mechanism could be seen depending on the tip's form. For both figures, measurements have been performed across the basin, which is extraordinary. On this slide, the patented device called penetrometer is shown. In the reference paper of 2018, one could find more detail about the device itself and the actual method of the measurement used. To achieve better understanding, authors suggest to refine the term hardness. In addition to resistance of area of the material surface to elastic and plastic deformation during quasi-static indentation, they suggest to use maximum resistance of its local volume to brittle fracture during dynamic immersion of the indenter over the entire thickness of the ice field. At the Krylov Research Center location, the modeled ice was prepared in a special way. It was frozen on 3 sides to the bores of the pool by spraying the salt water at low air temperature. As a result, mentioned on the slide strength value were observed. It also includes low modulus of elasticity and high homologous temperature. This slide presents fine crystalline structure of FG ice in polarized light, which allows to see actual ice crystals. It is important that it is also getting confirmed by experimental data, as shown on the next slide. This data strongly suggested the formation of secondary texture as a result of severe plastic deformations and metamorphism. Measurements are shown as dependency of force alongside the basin coordinate in meters. Authors brought for consideration 2 reasons of periodic structure formation: general loss of stability as the elasticity of structure with wavelength of 5 meters, and local loss of stability with wavelength of 2 meters. Measurements showed R hardness in kilopascal across the basin in meters. In the longitudinal direction, different wavelengths were observed, 2 and 40 meters. More detail about curve 2 are later on Fourier analysis slide number 17. Measurements shown are similar to the previous slide. Its hardness, but coordinate is along the basin. Authors found a very visual, 3-dimensional representation of experimental data, as shown on this slide. All observed wavelengths could be easily shown. Most important intermediate analyses are presented as periodic changes in hardness, which shape is a superposition of oscillation of substantially different periods. From possible causes, authors would suggest to concentrate on internal interrelated factors as stress state of ice, thermodynamic processes in the ice cover, the hardness of the ice frame, and adhesive contact of ice with the rigid walls of the pool. Two reasons for the formation of a periodic structure. Constructive reason, the wavelengths of 5 and 40 meters are determined by elastic properties of the original ice structure, like elastic mechanism of plate buckling. And the second one, texture or material, the plastic mechanism of buckling. Now authors would like to switch to the river basin measurement data as presented on this slide. Here one could see differences in hardness along and across perpendicular river flow. There is a potential relation between elastic and plastic processes and the loss of the stability. The phenomenon of periodicity of strength has been previously observed in the Becker with co-author paper of 2017, as mentioned. It is likely that the cause for sea ice is similar to the tested simulated ice. As conclusions, authors discovered the effect of periodical variability of the hardness of the ice cover. With the proposed hypothesis that the reason for the occurrence of the periodicity of hardness is the loss of stability, this could be potentially used for other ice conditions and applications. Then there is an assumption about connection of these periodic processes with ice thickness. More thickness believed to result in a less intensity of observed processes. Two identified reasons for the formation of periodic structures: loss of stability as a result of elasticity and by the elastoplastic mechanism. The considered effect can cause a scatter of the experimental values of the ice strength obtained at different points of the ice cover, which should be normally also taken into consideration by other experiments. And authors would like to present some interesting figures, more details on which are available in their recent papers. Here, the rheologic equation, there is no consideration for inertia. These are examples of so-called plastic waves. Here you can see zones of increased plasticity. Authors would like to thank you for participating in this presentation. Below you can find emails of authors for eventual questions. Thank you.
Okay, then I think we conclude this session. It's a few minutes into the coffee break, and probably get a small break before we get to the next session. So thank you very much to the speakers.
Thank you. For you.
We have, I guess we can keep the room and talk a bit if you want to, if somebody wants to do that. But the session is now closed, and we have a coffee break.
Yeah, it's good. Yeah, it's all good to talk because now it's not so much possibility to communicate.
This periodicity talked about, is it because the ice cover is deflecting? Or I didn't quite understand the... They drop something on the ice, or do you penetrate? I didn't quite... I can understand.
No, he thinks that maybe ice buckling during the formation.
Okay.
I read something about that in the tank. I saw their paper about freezing of water in the tank.
Mm-hmm.
But then he talked also about river. But what means periodicity? Of course, we always measured some oscillations of strength.
Hmm.
You remember it was discussed with Carl, and students measured special variations of ice strength. It all exists. And if you would measure over bigger scale, you could perform Fourier analysis and distinguish some periods, but it does mean that they are that is periodic. It is just changing in time.
Yeah, no. But he writes here in chat that it's about penetration. So they probably find that the ice itself has some kind of a spatial variability, which is systematic in the tank. And then it could be, like you say, it's due to freezing in conditions that it produces some conditions that gets a systematic. So across the river, they didn't find any strength, but it's just variations, but along they did. So.
Yeah, but of course, that's, we know that pancake is formed.
Yeah.
And then pancake is frozen. So then, of course, could be some periods, special periods because of that.
Yeah. And in this case, I guess they measure only on the surface because they drop this, it's limited how far down it penetrates. So it gives an characterization of the surface layer.
Yeah, that because he has this device which just you shoot in the ice and then use some analytical solution from viscous elastic materials or viscous plastic to calculate rheological constant. And of course, it cannot penetrate deep into the ice because it is a relatively small device. But of course, possible to drill and then to make it on different depths. It is like dynamic bore hole jack.
Yeah. Well, he writes in the chat again that it's about variations to forming conditions. So they think that the ice forms, and then it's quite interesting. It's
Yeah. So then.
Knut, in the previous session, you documented a project on fatigue. Is that still ongoing, or you finished that?
Just finished, but the work in a way continues. We didn't, so because we have a PhD student which was not connected or not paid by the project, and Hayo is already have another project. So at least the thing with offshore wind and ice, we continue with the resources we have and trying to get more and more funding. But there's one thing left in the project that we haven't done yet because of COVID and everything. But one of Hayo's PhD students will do it because we did some sharing with money, and that is to try. So they've now made a system where they can take these ice conditions and they can get fatigue life estimations. So now we're going to try to look at the uncertainty in ice conditions and see how that propagates and makes what consequence it has. Because we know, I mean, the ice thickness can be 40 or 30, or I mean, there are some uncertainties. There is quite a large uncertainties in ice conditions. And how do these propagate and give a changing fatigue life estimation? That's left to do, and we'll do this whenever time allows during the autumn. That will be nice, and then we should probably try to write a journal paper or something about it. But there are some papers from IHR last year and POAC last time about this, and so then we.
Where is the next IHR?
It is in Canada.
Montreal.
Oh, right. That's right.
It's organized by by the CREEPE organization. So it's Amy or Yung Tong Shi who organizes it. So that's in Montreal. So that will be nice, and I guess hope we'll be getting there.
Yeah, well, it's easy for me to get to. I'm right now. I'm less than an hour's drive from there. It's easy.
Yeah, it was very nice in Montreal when we had POAC. I liked the city. It was, I don't know, it felt good.
Yeah,
long trip, but still it was.
Yeah,
that's my home city. That's where I grew up.
Okay.
Are you now in some countryside?
Well, yeah, I could turn the camera out the window. It is in the country.
Yeah.
But I'm here watching over it's my mother's family home that I'm taking care of right now.
Yeah.
Ah, Sergei.
Hey, I was watching your sitting there for quite a while.
Okay.
Never changed during the last 2 years, right?
No.
Yeah, so you're busy with ice things in Kazakhstan, Sergey?
Yeah, it's kind of a lot of internal research that we are doing now.
How was the ice conditions in this winter in Caspian Sea? Can you hear?
Yeah, I'm trying to think how I can actually show that.
We couldn't hear your response. It was a little bit muffled.
I was trying to think how to show that. It's actually funny. We're talking about all this global climate and stuff, but all of a sudden we have quite a cold winter, and it's, I don't know. No, we have looked into quite a bit of ice conditions in the history of the whole Caspian, and our database is quite expanded now, and we can see it it's quite a normal, which seems to be a very harsh winter now, but it is an average compared to 10 years ago.
We had the last winter very cold and thickest ice over the last 15 years. And this year ice was usual as was. So this winter was very long, but not very cold.
Yeah, we can see that there is some sort of a shift taking place. We have now earlier winters and earlier ends of winters. So this is something that I can't see the explanation yet. Yeah.
Looks like you're convener on the next session there.
Yeah, that's me.
It's coming up soon.
If you can see my screen there.
Yes.
That's what I meant. We have found out that there is a sort of 4-year cycle, going 2 severe winters, then there's 2 milder ones. And we're looking now into earlier years, which are not filled yet. But this seems to be the coldest that we can expect in the Caspian. So who knows?
But last winter was quite amount of ice was small.
No, this is the ice volume, so it's really big. Average ice volume for the season.
So that's quite big. But last winter, 1920, was small.
This was extreme mild.
Yeah.
It's like the mildest in 100 years or something.
Yeah.
So
I think we have some sound problems. I don't know where it come. where from it is coming. Some echo.
Yeah, maybe I should turn off something here.
I don't hear any echo, so I'm not sure if it's.
No, I could hear that someone on your session didn't turn off the sound from the session, and you could hear what was on the other session.
Yeah, that
So
was.
the mic wasn't off, and we could continuously hear.
Yeah, somebody use two computers in the same time.
Yeah. Now I see session 2 is starting, so I will leave this room and listen to the to session 2. So then you may start your session, Sergey.
Thank you. Maxim? Maxim, вы не могли бы, could you switch on the mic and show the presentation title? Share the screen.
Good afternoon.
No, we start in 5 minutes.
Okay.
But could you set up the presentation?
Okay, just a minute.
Share it on the screen so that we can see it.
Do you hear something? I don't have any sound.
No, we're waiting for
Okay.
2 more minutes to start the session.
Okay.
So I think I could do some introduction. This session is on problems of construction of oil and gas platforms, underwater pipelines, and coastal structures. My name is Sergey. I'm from Kazakhstan. And the first presenter today is Maxim Muratov from Moscow Institute of Physics and Technology. And we will now hear about numerical modeling of elastic and thermal dynamical processes of ice islands. So Maxim, take over.
So I can start.
Yep.
Dear colleagues, my name is Maxim Muratov, and my report today is numerical modeling of elastic and thermodynamical processes in artificial ice islands. Firstly, we will talk about problem formulation in problems of ice island. I describe the studied process which we modeled. Then I will talk about elastic model of ice island, which was used in simulation. Then we will discuss thermodynamical model for ice island, and then we observe the results obtained during the mathematical modeling with use of this elastic and thermodynamical model. Arctic region is quite rich in minerals, especially oil and gas. So its exploration is quite important problem. Artificial ice island is good alternative to traditional drilling equipment because of their ecological factor and low expenses. But ice islands have some problems in comparison with traditional equipment, such as bigger sensitivity to mechanical impacts and influence of seasonal temperature change to ice islands. These problems are studied with use of mathematical modeling in this report. So we study the ice island of depth 10 meters and longitudinal size of 300 meters. The model of integrational domain is represented on the slide on the left. There are ice layer with water around it, bottom layer, above the ice layer, sedimentary rock, and gas-bearing layer. In these layers are taken into consideration during elastic modeling. In thermodynamical model, we take into consideration just bottom layer and layers above it, so without sedimentary rock and gas-bearing layer. The physical characteristics of these layers are represented on the right part of the slide, such as longitudinal wave velocity, shear wave velocity, density of medium in the layer, thermal conductivity, and specific heat capacity. So elastic model is represented by a linear elastic medium, which consists of governing system of equation of linear elastic medium, local moving equation, and Hooke law. This system can be represented as hyperbolic equational system and can be solved by grid characteristic method, which is more suitable for such problems. Drill is modeled by point source with recur impulse. Destruction model is represented by a field of von Mises stresses in each point of ice island. We find the stress of von Mises by this formula and compare it with shear stress limit, which is for ice is equal to 1 megapascal. If stress of von Mises is more, then shear stress limit so in this point is some destruction. Thermodynamical model is based on first law of thermodynamical. Also we use Fourier law of heat conduction. Finally, the system equation system can be represented by this formula. For numerical solution, we use Pisman-Rykford numerical scheme. We study three models of ice island for thermodynamical problems. First model first model doesn't take into consideration water flow and has constant ground temperature, which is equal to 5 Celsius degrees. Second model is model with constant ground temperature, and it takes into consideration water flow. Model 3 is model with water flow and with freezing of ground. So it takes into consideration also the change in temperature of ground. Okay, this slide, and on this slide, the results of modeling for impact of drilling to ice island are represented. There are velocity fields of drill impact in different time moments. Also, for this problem, velocity fields are observed and stress fields. On this slide, we can see the results of modeling for static load. The building with mass of 100 tons and dimension 5 to 5 meters is placed on the top side of ice island and makes some pressure for ice island. On the slide, the fields of components of stress tensor are represented. This, and this, and field of Mises stresses for ice island with building of 100 tons. So the maximal for Mises stress was equal about 2 kilopascal. That is significantly less than limit of shear stress, which is equal to 1 megapascal. So the ice island, is not destructed in such problem. Static load distribution was found by relaxation method. After 200,000 time steps, velocity magnitude was stay on some the same factor, so resulting stress distribution is stable. The next slide is on the next slide the results of temperature distribution after ice island construction are represented. The temperature of air was minus 12 degrees of Celsius. The temperature of water was about 5 degrees and temperature of ground was about 5 degrees. On the top part of slide, the temperature distribution is represented with isolines, and bottom part of slide is on the bottom part of slides. The phase map is represented. Where can we see the phase states of medium as water, ice, or ground. For first and third model, as third model takes into consideration freezing of ground, bottom part of this figure is represent the ground. On this slide, the results of modeling for seasonal temperature change for 3 models. We replaced the ice island into the medium with air temperature 10 degrees Celsius degrees, and for 150 days, and observe the temperature distribution and phase map after this time period. The results are represented on this slide. So, in conclusions, I can say that numerical experiments to test artificial ice island stability to static and dynamical mechanics loads and resistance to melting are discussed. Approach based on grid characteristic method can be used for modeling of elastic impacts for ice islands and modeling of ice island stability. And approach discussed approach for thermodynamical processes can be used for such problems. So thank you for your attention. Your questions.
Sergey, do you have something?
Let's wait for questions on the YouTube channel. Meanwhile, we don't have the second presenter, so we can talk a lot about this one. And let's think of the questions. in your numerical modeling, did you think of particular geographical area where you used time series of air temperature?
Sorry, could you repeat, please?
This modeling was done for some particular geographical region.
Mm-hmm. It's we take the characteristics of Yamal shelf.
Yamal. Yeah, well, perfect FDD. And this is for shallow waters, because I haven't seen any particular water depths there.
But I think that other regions has the same, but other regions can be modeled by such model by changing some parameters.
Well, I come from a practical world, and in some regions there is not enough freezing degree days to actually construct the island or drilling activity. So now the artificial ice islands were used in Canadian Arctic, where they have sufficient freezing degree days to actually freeze a lot of water, so that you submerge ice layer by layer into the water and maybe ground it on the seabed. But in a lot of cases, it actually remains afloat, because you don't have enough time to freeze enough water so that you could put the drilling rig on top of it, for example. That's just a general comment. Alexei?
Yeah.
From the mathematical point of view, do you have any questions?
Yeah, I was thinking that maybe, did you think about a laboratory experiment?
No, in this moment there are no laboratory experiments, but in plan we will do it.
Yeah, because for water, what model did you use for water?
Water is acoustic medium in elastic model and in thermodynamical model. The model with
you may have turbulence.
No turbulence. In elastic, it's important in elastic model. There are no turbulence in.
Yeah, but then heat transfer in water could be underestimated, because you use molecular thermal conductivity, but in real situation you may have advection, some currents, and it will increase heat flux to the ice from the water.
Okay.
I think in the experiment you would see that clearly.
In thermodynamical experiments, okay, I will think about it. We in thermodynamical experiments we take into consideration just water flow.
Yeah, but, okay, so that was my comment.
So I think these are all the questions. We will not have the second presenter. Anna Denisova has not showed up, and we start to Ivan Marchenko is preparing to share the screen to present the features of engineering surveys and leg penetration analysis for drilling platforms in the Arctic seas.
Hello, can you see my presentation?
Yeah, the presentation is on. We can hear you and we can see you.
Okay, thank you. Здесь вот выключить. Thank you. Hello, dear colleagues. My name is Ivan Marchenko, and I present the Marine Arctic Geological Expedition Company and Gubkin University of Oil and Gas. I'm a PhD student at this university. Today I would like to present a presentation for features for geological surveys and leg penetration analysis for drilling platforms in the Arctic seas. To start, I would like to mention that the exploratory and prospecting wells are the necessary components for hydrocarbon field development. Nowadays, our Arctic shelf is the most important, one of the most important directions for offshore hydrocarbon exploration projects in Russia, and exploratory works, prospecting wells drilling, and engineering surveys are the operations which are currently actively performed in Russian Arctic shelf, in Barents Sea, mostly in Barents and the Kara Sea. From our side, from engineering survey side, we in the recent years, we have performed a wide range of works at the sites for projected drilling wells and locations for drilling rigs positioning. So the relevance of the current research is the following positions. At the moment and in the near future, as I mentioned on the previous slide, the development of the fields in Arctic is on the stage of exploration and prospecting drilling. Drilling now is performed mostly from platforms such as jackup rigs and semi-submersible. Both Russian and foreign platforms operate in Russian Arctic. When we perform the engineering surveys and the positioning of the platforms, we meet with the lack of ordinariness and regulated algorithm of performing the engineering survey for offshore oil and gas facilities. We also have a lack of an actual standard and regulations for geotechnical calculation of drilling platforms. Of course, we have international standards like ISO and SNAME, but in Russia we don't have an actual standard, and we use other standards for calculation. And also there are difficulties in the coordination of participants of this process in the algorithm of works, in areas of responsibility, and in the applicable standards. When we have a project for prospecting well and the engineering survey for site of the prospecting well, we have different participants like listed below on the current slide: the client, the engineering survey contractor, designer, insurance company, drilling contractor, ship owner. All of these participants can be from different countries, can use different standards, and this can be a big problem in coordination of all these participants and the used documents. Well, so we have the survey objectives on the current slide. It's the main is to improve the reliability for drilling platforms positioning in Arctic seas and to develop a scientifically grounded approach in integrated engineering survey on the shelf and geotechnical calculation in order to minimize the impact of natural and technogenous hazards and ensure the safest and most economically profitable positioning on operation of the planned drilling platform in Arctic seas. The next part of presentation, in the next part, I would like to talk about the causes for the accidents which happen with the jack-up rigs and the causes for these accidents. So, well, in the current slide, I listed the causes, main causes for accidents with jackups. It's wellbore heating zones of abnormally high reservoir pressure and subsequent gas flowing and fire. The next one is gas release and formation of a funnel or a pockmark with subsequent failure of one or more jack-up rig legs which meet this pockmark. It's the wrong calculation of designed leg penetration. When it was designed, it was planned that the penetration will be 5 meters, and it is suddenly 10 meters. This is a problem. The second is additional rapid penetration of a leg, so-called punch-through. It's a result of falling into a zone of insufficient thickness of a bearing layer of bottom soils in foundation. So the leg goes through this layer or presses this thin layer in under bedded weak soils. And the second cause is rapid penetration due to increased loads during a storm. Then it's a spotcan slide, and due to irregularities on the seabed, its course, its footprints from the previous jack-up position, and the next is the instability of the seabed. Mud flow, underwater landslides, if it's a slope, any volcanic activity, for example. Here it's the example of emergency situation of jack-up rigs with the indication of location and what happened in the accident. We see that the last two positions happened in previous months, in May of 2021. And the cause was the rapid penetration of one leg and the subsequent hull flooding. So we see that these problems happens 20, 30 years ago and nowadays. And so this is still a problem. Here we see the illustration of such an emergency situation on jack-up rig in 2007. It happened in the Gulf of Mexico. Also, the rapid penetration of a leg, the subsequent hull damage, and the fire. Here we see an accident on jack-up Perro Negro 6 in 2013. Also, punch-through, hull damage, and fire. And here we see that the accidents can occur not only in the open sea on the field, but it can happen even in port, close to a quay. We see that there were a situation when the leg matched the footprint from the previous jacket brake position, and the one of the legs of jacket went to further additional penetration. Yes, the next part is the list of geological hazards. So we have talked a bit about the causes and the accidents, and now we move to the hazards, which can be hazardous to the jacket. It's a gravity process, it's soils with accumulation of gas, it's presence of weak gas-saturated soil, it's presence of frozen soils. It can be a permafrost or insular permafrost, metallic zones. It can be liquefaction of surface salts, rock relief, iceberg trade, extreme climatic loads, and impacts. The goals and objectives of engineering survey for safety position of drilling platform are the following. It's a determination of a location for safe positioning of a platform and obtaining of geological data for quality geotechnical calculation for a platform. So we first select the location, the correct location. We one or two locations, and then on this location we need to get the geological properties for calculation. So the objectives consequently are the determination of the natural processes, natural geohazards, the study of geological profile, including composition, structure, property, state, and condition of soil bedding. The engineering survey are to be performed in a complex approach. We have to perform both typical and special methods for engineering survey. It's geophysical, it's hydrographical, it's engineering geological survey, and engineering hydrometeorological and ecological surveys. Above the mentioned typical methods, we have specific engineering survey methods which are performed in the Arctic regions. It's drilling with the downhole thermometry. It's soil sampling and testing in offshore laboratory with the specific number of special laboratory tests. And it's geotechnical methods. It's cone penetration testing with measurement of thermophysical and electrophysical properties of soils. After we have performed the complex engineering survey, we have to perform the integration of the research results. Here we see the example of integration, results integration for frozen soils. We see the drilling profile, geological profile for after drilling. We see the graphs for thermometrical investigations, and we see the profiles from geophysics. After that, we have to perform the natural hazards mapping, and we have to correct the location of the well and prepare the reserve well location. When we talk about the geotechnical properties and the engineering geological investigations, we have to take into account that the soil properties can be obtained by different methods, and both field methods and laboratory methods have to be performed because in order to obtain the wide range of properties and to have a possibility to compare and perform different calculations with different properties and have a possibility to compare the results. So we have to perform the various methods to determine the key soil properties. Also would like to mention that the Arctic shelf is often characterized by large lateral soil variability. So let's see, it can be different thin layers, 5-10 meters to side to side. So the drilling for each leg, when we talk about jackups, it has to be performed. When we have obtained the geological properties, we can move further to calculations for platforms. For jackup rigs, we perform the stability assessment, leg penetration analysis, and analysis of the applicability of platform position inside. For semi-submersible, it's mostly calculations for the anchors. We will move further with the jackup rigs analysis. We have here the standard base for penetration testing. It's Russian standards. It's some old Soviet guidelines. It's of course the actual standards, international standards, NAME and the ISO. Here we present the scheme, the solution for generally for geotechnical geotechnical calculations for gas facilities and for jackup rig. So first of all, we have to design a jackup platform SPATCON model. Then we have to design a soil profile model and then perform the leg penetration analysis. After that, we have to consider the additional factors and correct the penetration analysis results. Here we can see the methodology for penetration analysis. In Russian standards, we have both stress and deformation analysis. In ISO and SNAME, in international documents, only a stress analysis is performed. So we make the computation of bearing capacity and then, of course, including all the factors. Then we plot the vertical bearing capacity curve and compare it with the maximum preload. Here we have the formulas for calculation of bearing capacity in Russian standard and in the SNAME. We see that in the Russian standard we have a larger formula. It's a single for all soils, and SNAME we have two formulas, one for clays, one for sands. We see that the bearing capacity factors marked with red and the yellow circles are identical, almost identical for both Russian methodology and the SNAME. But the formulas how these factors are calculated these are different, and that's why the result, the number which we get, the value of the penetration, it can often be quite different. Also in the SNAME, we have to take into account that they are taking into account different factors like soil backflow, like additional calculation for punch through and squeezing, and thus we get like most more like more pessimistic calculation in the result. Here we can see how the soil backflow happened. It can be caused by different reasons, by cavity wall collapse, sediment transport, squeezing of the soil under the spotcan and flow over the surface. Yes, then we move to illustration of punch-through effect. How it can happen. The reef starts to rise under the water. It's now preloading state, and you see that suddenly one of the deck get a rated additional penetration, and of course it will be a large platform. It will be a serious accident, emergency situation. And here we see the presentation of a curve with the geological profile, and we can see Jacob Spotkan here. And then after we have performed the calculation, we can compare the results. The typical difference is presented on the current slide. The calculation performed by Russian SP and according to SNAME. We see that in SNAME, the penetration will be like about 6.57 meters, and in Russian, the bearing capacity is higher, and it stops. The predicted penetration is about 3 meters, so it's almost 2 times larger penetration. Here we can see that it's the illustration of another situation when we have sand layers, and we, of course, if we have a strong thick sand layer, the result will be similar. But what is have to be mentioned that the SNAME result shows the larger penetration values almost in all cases. So the closer to actual value when the platform starts the positioning and the preloading, the results for Russian method gets give the value of penetration closer to the actual. Also, I have performed some calculation and analysis in an element program package called the Midas GTS NX to check the results and to get the more precise values. So we have developed a method for calculation in this program package. We have a typical model here with the geological profile spotcan of Jacob Frey, the load from the platform, the water surface, and here we have the typical image presentation of the results. So we have displacement here. So yes, it's a good instrument to to make a checkup for numerical calculations, and is also to be performed. Yes, and finally, I'd like to mention some conclusions and recommendations for this work. We have presented the accidents and the causes for the accidents on Jacob rigs, which can happen in Arctic seas and in other seas. We have analyzed the natural hazards, which can occur during the platform positioning and operation. We have presented the methodology and the algorithm of actions for engineering surveys. The complex approach has to be performed. And we have the geotechnical calculations, which have been performed according to different standards and different methods, and have been compared with the actual value of the penetration, which have been which we have got after the positioning on the platform. And as a result, we have to mention that the calculation with the Russian methods show higher convergence, and the foreign methods show larger values, and thus reflect the most pessimistic scenario of leg penetration. And we have to say that it is better to take into account both pessimistic and optimistic account. They have a range of the penetration values to and this information is to be given to the drilling operator, and the drilling operator has to take into account that it can be a range of penetration depths. Thank you very much. Thank you for listening.
Okay, thank you very much for your presentation. And from YouTube, Dmitry Anishenko, thanks as well for a very interesting talk. And he has a question from your field experience. Have you observed any particular parts of the Russian Arctic shelf that are especially risky for drilling with jackups? Or is this risk that you are talking here about is absolutely random?
Thank you for the question. As I mentioned on one of the previous slides, Arctic shelf, and mostly in my research, I investigate the northwest shelf of Yamal Peninsula, so it's Kara Sea. So there we have a difficult situation. It's lateral difference of soils. So as I mentioned, it's necessary to drill the boreholes for each leg because 5, 10, 15 meters to the side, and we can meet the completely different thin layers which can cause the unpredicted penetration. Of course, it is there are some difficulties with the gas separated deposits because it is difficult because the signal from geophysics from vessel when we perform the geophysical investigation, the signal can't go through these deposits, so we can't. It can happen that we have not investigated one or more hazards. So to answer this question, of course, the shelf of Kara Sea, the North Sea shelf, is difficult. But when, in case if we perform the quality engineering survey. If we do the complex approach, if we integrate the results, it can be possible, and the positioning of the rig can be safe. But of course, generally, the Arctic Shelf for positioning of the jack-up platforms is quite difficult and problematic and hazardous.
Okay, thanks a lot. And that finishes the day of PORC with the last presentation in this room. With it. Thank you very much, Ivan. I think we should leave the room, and we will stop the record.
Thank you. Thank you.
Bye.